A map of the universe. Unknown. A map of the universe reveals. A new map of the universe has revealed something that shouldn't exist. A massive hole where matter seems to be missing. This gap defies everything cosmologists expected, challenging our understanding of space, time, and the very structure of the cosmos. The universe as data. There was a time when the universe was described almost entirely through language and invisible forces that pushed and pulled in ways no one could see. But that era quietly ended once telescopes stopped being tools for looking and started becoming machines for collecting numbers. Because the modern universe is no longer something we simply observe with our eyes, but something we measure, catalogue, index, cross-reference and rebuild again inside computers, where space becomes coordinates, light becomes values, motion becomes trends, and the sky turns into structured information that can be tested again and again without ever pointing a telescope back up. Today, when scientists talk about the universe, they are not talking about maps built from trillions of data points, where every object is placed inside a system that records where it is, how far away it is, how fast it is moving, how bright it appears, and how its light has changed during its journey through expanding space. Because only data can handle a universe this large without collapsing into guesswork. The shift happens slowly, starting with star charts and catalogues, then photographs, then digital images, and finally full sky surveys that treat the universe less like a scene to admire and more like a structure to measure. Because once astronomers realized that individual objects could lie to you through chance alignments, dust, and distance tricks, they learned that meaning only appears when everything is seen together as part of a larger pattern. In this data-driven universe, galaxies are no longer just distant islands of stars, but entries in a vast database, each one tagged with properties that can be compared across millions of others, allowing scientists to see what repeats, what clusters, what spreads out, and what breaks expectations, because patterns do not show up clearly when you stare at one object at a time, but they become obvious when the entire sky is turned into structured information. This is why modern cosmology begins with maps rather than images, because images show beauty while maps reveal behavior, and behavior is what tells scientists how the universe is built and how it changes over time. Maps are not drawings in this context, and they are not artistic choices or visual summaries meant to make things easier to explain, because these maps are mathematical constructions where every point comes from real measurements collected by instruments designed to remove human bias as much as possible, turning the sky into something closer to a spreadsheet than a painting. Each map is built layer by layer, starting with raw light collected by telescopes, which is then broken down into numbers that describe brightness, color, position, and movement, after which those numbers are cleaned, corrected, and aligned until the entire sky fits into a single coordinate system that allows every galaxy to be placed relative to every other galaxy. When cosmologists look at these maps, they are not asking what the universe looks like, but how it is arranged, because structure reveals history, and history reveals the rules that shaped everything from the first moments after the universe formed to the way matter gathers today. Words struggle to handle this scale because language is linear while the universe is not, but maps allow scientists to see many relationships at once, showing how galaxies cluster into filaments, how voids stretch between them, and how these features repeat across enormous distances, forming patterns that could never be noticed by focusing on a single region of the sky. These maps are not static either, because new data constantly flows in, filling gaps, refining distances, correcting errors, and sometimes revealing features that were completely invisible before. Which is why modern cosmology treats maps as living objects that evolve alongside the technology used to build them. The power of maps lies in their ability to compress the universe into something that can be tested, simulated, and challenged. Because once the universe is mapped, it can be compared against predictions, and mismatches stand out sharply without needing dramatic interpretation. Sky surveys as time machines. A sky survey is not a single image or a snapshot of the universe frozen in one moment, but a layered record of light that has been traveling for different lengths of time before reaching Earth, meaning that every direction you look represents a different chapter of cosmic history, even though it all arrives at the telescope at the same instant. When astronomers plot the results of a sky survey, every dot on the map represents a galaxy. But that dot is not just a location, because it carries with it information about how long its light has been travelling, how much the universe has expanded since that light was emitted, and how the galaxy fit into the structure of space at that earlier time. Colour becomes a critical tool here, not for beauty, but for meaning, because colour in these maps often represents redshift, which measures how much the wavelength of light has been stretched as space itself expanded, allowing scientists to convert colour into distance and distance into time without ever needing to physically travel there. A galaxy shown in one colour might represent light that left when the universe was younger, denser, and more tightly packed, while another colour represents a later era when space had stretched further apart, meaning that a single map can quietly contain billions of years of cosmic history encoded in gradients that look simple but carry enormous weight. This is why sky surveys function as time machines, because they allow scientists to reconstruct how matter arranged itself across different eras by comparing nearby galaxies with distant ones, revealing whether patterns remain consistent or change as the universe evolves. When these surveys are combined across the entire sky, they produce a three-dimensional view of the universe where position, distance, and time merge into a single structure, making it possible to trace how galaxies moved, clustered, and separated under the influence of gravity and expansion. Each dot may look small, but together they form the scaffolding of the cosmos, and when millions or billions of these dots are placed together, they reveal whether the universe behaves smoothly or hides irregularities that only appear at extreme scales. The universe is not flat in the everyday sense, and it is certainly not easy to represent, but cosmologists still need a way to turn a curved, expanding, three-dimensional reality into something that can be stored, shared, and analysed, which is why they flatten it into datasets that strip away visual complexity while keeping physical meaning intact. This flattening does not mean removing depth, but translating depth into numbers, where distance becomes a value, direction becomes a coordinate, and brightness becomes a measurement that can be compared across the entire sky without distortion caused by perspective or scale. To do this, scientists choose reference frames that account for Earth's motion, the motion of the Sun, and the motion of the galaxy itself, because even standing still is an illusion in a universe where everything is moving relative to everything else, and failing to correct for that motion would warp the map in subtle but damaging ways. Once those corrections are applied, every galaxy is assigned a precise position in a coordinate system that allows it to be plotted alongside millions of others, turning the sky into a massive table where relationships become easier to measure than they would ever be by eye. This process allows cosmologists to run calculations across the entire universe at once, measuring average densities, spacing between structures, and large-scale patterns without being distracted by local oddities that might dominate a smaller field of view. Flattening the universe into data also makes it possible to simulate alternate universes inside computers, where scientists can tweak initial conditions and watch how structures form, then compare those simulated maps to real ones to see which models survive contact with observation. Without flattening, none of this would work, because raw images alone cannot reveal subtle trends that stretch across hundreds of millions of light years. But datasets can, as long as they are built carefully and consistently. Why large-scale maps are trusted more than any single telescope image. A single telescope image can be breathtaking, but it can also be misleading, because chance alignments, dust clouds, and local variations can create patterns that vanish the moment you zoom out, which is why cosmology places its trust in maps that average across vast regions of space rather than isolated views. Large-scale maps reduce noise by sheer volume, because random fluctuations cancel out when enough data points are included, leaving behind structures that reflect real physical processes rather than coincidence. When millions of galaxies are mapped together, it becomes possible to measure how matter distributes itself statistically, revealing whether galaxies cluster more strongly in certain directions, whether voids repeat in size, and whether patterns appear consistently across different parts of the sky. These maps are also built from multiple instruments and surveys, which means the same structures are often detected independently using different methods, reducing the chance that what is being seen is the result of a single faulty sensor or processing error. Trust builds when separate data sets agree, especially when those data sets come from telescopes operating at different wavelengths, because light that behaves differently across the spectrum still traces the same underlying structure, if that structure is real. Large-scale maps also allow scientists to test their assumptions directly, because predictions about uniformity, clustering, and spacing can be measured quantitatively rather than argued about subjectively. This is why cosmology advances through maps rather than images, because maps make disagreements visible in numbers rather than opinions, and numbers force clarity where words might soften uncertainty. Every cosmic map begins with an assumption so basic that it often goes unstated, which is the idea that when viewed at a large enough scale, the universe should look roughly the same in every direction, without preferred regions, special centers, or massive irregularities that dominate the whole. This assumption does not claim that the universe is smooth everywhere, because galaxies clearly cluster and voids clearly exist, but it does claim that these features should balance out when averaged across enormous distances, producing a universe that behaves predictably when examined in bulk. Uniformity at scale is what allows cosmologists to use statistics at all, because without it, measurements from one region could not be compared meaningfully to another, and maps would lose their power to reveal universal laws. When scientists flatten the universe into datasets, they are implicitly testing this assumption, because any deviation becomes visible as an imbalance that refuses to disappear no matter how much data is added. This assumption is not philosophical or aesthetic, but practical, because the entire framework of modern cosmology depends on the idea that the universe does not play favourites when viewed from far enough away. Every sky survey, every redshift map, and every large-scale dataset carries this expectation quietly within it, waiting to be confirmed or challenged by what the data actually shows once everything is plotted and aligned. And it is precisely because maps are trusted, comprehensive, and built on this assumption that any large-scale feature that refuses to blend into uniformity immediately demands attention, not because it is dramatic, but because it threatens the foundation that makes mapping the universe possible in the first place. The moment the map broke. For decades, cosmology moved forward with quiet confidence, not because scientists believed they understood everything, but because every new map kept agreeing with the last one closely enough to reinforce the same broad picture, a universe that clumped and spread in familiar ways, a universe where strange things existed locally but faded into balance when viewed from far enough away. And then one region of the sky refused to behave, not loudly or suddenly, but stubbornly, appearing wrong in a way that did not vanish when the data improved. The first hint arrived as an uncomfortable shape in a dataset that was never meant to show shapes at all, because the survey that revealed it was designed to measure temperature differences across the sky, not to hunt for missing matter or broken structure. And yet the map displayed a region that looked quieter than it should have been, dimmer than surrounding space, and too large to ignore. This was not the kind of discovery that makes headlines immediately, because nothing exploded, nothing moved, and nothing shone brighter than expected. But inside the data, there was a hole where the universe seemed to thin out beyond what the rules allowed, and once that hole appeared, it refused to go away. The moment the map broke was not a single day or a single press release, but a slow realization spreading through teams of researchers who kept asking the same question from different angles and receiving the same uncomfortable answer, that something was missing, and not just a little. The first crack appeared in data from WMAP, a spacecraft built to study the faint glow left behind by the early universe, mapping tiny differences in temperature across the entire sky with the goal of learning how matter was arranged long before galaxies formed. And when its maps were released, they matched expectations almost perfectly, except for one region that looked colder and smoother than the rest. At first, this feature did not raise alarms, because cosmic maps are filled with small oddities, and early data always carries noise, calibration limits, and foreground interference. But the scale of this region made it hard to ignore, stretching across a wide patch of sky with a shape that felt deliberate rather than random. Researchers assumed the feature would soften or vanish as more data came in, because that is what usually happens when resolution improves. But instead, as WMAP gathered more years of observation, the feature stayed in place, keeping its size and position, while the rest of the map sharpened around it. Then came Planck, a mission built to outperform WMAP in every way, with better sensitivity, finer resolution, and improved control over errors. And when Planck released its maps, the expectation was simple: that any questionable features from earlier surveys would be clarified, smoothed out, or explained away. Instead, Planck showed the same region again, not blurred or weakened, but cleaner, more defined, and harder to dismiss, because it now appeared in data collected by a different instrument using different methods, which removed the most comforting explanation, that the anomaly was a mistake. With Planck, the issue changed from curiosity to problem, because confirmation meant the feature belonged to the sky itself, not to a machine. And once that happened, attention shifted from temperature maps to galaxy surveys, which could test whether something physical in space lined up with the strange signal. Large galaxy surveys began to chart the same area, counting galaxies, measuring their distances, and mapping their distribution across space. And this is where the anomaly stopped being subtle, because where scientists expected to see a normal spread of galaxies, they found far fewer than predicted. The surveys did not show a clean, empty circle or a simple gap, but a deep, extended region where galaxy density dropped well below average across an enormous volume, a volume so large that random chance could no longer explain it. At this point, the anomaly had crossed a threshold because it now appeared in multiple forms of data, from temperature maps to galaxy counts, from different instruments across different years, and every new survey sharpened the outline rather than erasing it. Before the maps were drawn, expectations were clear, because cosmology had already built a strong picture of how matter should be arranged at large scales, with dense regions where galaxies cluster, wide voids where fewer galaxies exist, and smooth transitions between them that repeat across the sky without favouring any particular direction. In that region of the sky, scientists expected to see variations similar to those elsewhere, perhaps a modest void or a mild overdensity, but nothing extreme enough to stand out once averaged across hundreds of millions of light years. They expected galaxy counts to fluctuate within a known range, guided by simulations that had been tested repeatedly against observations, simulations that could reproduce the cosmic web with impressive accuracy when fed the same basic rules of gravity and expansion. They expected temperature patterns in the background glow to vary gently, shaped by early density differences, but smoothed over time, not marked by a single dominant feature spanning such a wide area. They expected that if anything unusual appeared, it would be balanced by something else nearby, because that is how large-scale structure behaves when the universe plays fair with itself. These expectations were not hopeful guesses, but results drawn from decades of observation and modelling, reinforced by the fact that most of the sky behaved exactly as predicted, making the anomaly stand out, not because the model failed everywhere, but because it failed so clearly in one place. The confidence in these expectations was what made the anomaly unsettling, because when a rule works almost everywhere, its failure in a single location becomes harder to dismiss, not easier. What appeared, instead, a vast underdensity. What appeared in the maps was not a simple gap, but a massive region where matter thinned out across a volume so large that it could swallow entire galaxy clusters without filling itself back in. a region where the number of galaxies dropped far below the cosmic average, for reasons no standard process could easily explain. This underdensity did not have sharp edges or a clean boundary, but stretched gradually, forming a deep basin in the distribution of matter rather than a hole punched cleanly through space, making it harder to describe and even harder to simulate. The scale was the most troubling part because smaller voids are common and expected. But this region extended across distances that pushed the limits of what structure formation models allow, especially given how late in cosmic history it appeared. The depth mattered just as much as the width, because the drop in matter density was not mild, but strong enough to affect how light travelled through the region, altering signals that passed across it in measurable ways. Galaxy surveys showed fewer galaxies, not because they were hidden or faint, but because they simply were not there in the numbers expected, and this shortage persisted even after accounting for observational limits and selection effects. The underdensity aligned with the earlier temperature anomaly in a way that felt too precise to ignore, connecting two very different kinds of observation into a single physical feature, one traced by missing matter and the other by altered radiation. As more data arrived, the underdensity became harder to shrink or soften, because better measurements tightened its shape rather than dissolving it, making it clear that this was not a statistical mirage. Calling the region empty would have been convenient because empty space requires no explanation. But the maps did not show emptiness in the simple sense, because space itself was still there, light still passed through, and the universe did not end or tear open in that direction. What was missing was matter, not space. And that distinction matters, because matter shapes how the universe behaves, how galaxies form, how light bends, and how signals change as they travel. Meaning that removing matter from such a large region alters the universe's behaviour in ways that can be measured. This was not a case of galaxies being too faint to see or hidden behind dust, because different surveys using different wavelengths all reported the same shortage, ruling out obscuration as an explanation. The region still contained galaxies, but far fewer than expected, and those that existed showed no signs of compensating for the missing mass, meaning there was no hidden population waiting to be discovered. Light passing through the region behaved differently, losing energy in a way consistent with a deep underdensity rather than an observational gap, confirming that the shortage was physical, not apparent. The shape of the region also argued against emptiness, because it followed the kind of gradual density change expected from structure growth, not the sharp cutoffs produced by survey limits or data masks. If it had been empty space in the trivial sense, the anomaly would have vanished once corrected for coverage and noise, but instead it grew clearer, tying itself to independent signals that had no reason to agree unless they were tracing the same physical structure. The problem was not that nothing existed there, but that too little existed there across too much space, creating an imbalance that refused to average out, even when the map widened to include surrounding regions. This is why the moment the map broke mattered, because the anomaly did not live at the edges of knowledge or the limits of instruments, but squarely inside the region where confidence was highest, forcing scientists to confront the possibility that something real had slipped through the cracks of expectation. And once the map revealed that break, there was no way to unsee it, because every new layer of data returned to the same place, pointing again and again to the same missing mass, sitting quietly in the sky, large enough to challenge the assumptions that made the maps possible in the first place. The cosmological principle explained. Modern cosmology does not begin with freedom, but with limits, because the universe may be vast, but the rules used to describe it are narrow, carefully tested, and unforgiving when pushed too far. And those rules define not just what can exist, but what cannot exist without breaking the structure that holds everything else together. At the core of those limits sits the cosmological principle, an idea so basic that it shapes every map, every model, and every simulation before any data is even added. because it states that when the universe is viewed at a large enough scale, it should look the same in every direction and from every location, not identical in detail, but balanced in behaviour, without massive favoured regions or giant defects that dominate the whole. This principle does not deny structure because galaxies clearly gather and voids clearly form, but it demands that these features remain statistically even across the largest distances, meaning no single region should be so extreme that it overwhelms the average behaviour of the universe itself. Uniformity at scale is not a belief, but a requirement, because without it, measurements taken from one direction could not be compared to another, and predictions would collapse into local descriptions with no universal meaning. Every model that describes how matter spreads through space assumes this balance, and every simulation that recreates the universe begins by enforcing it, because once the balance is removed, the math no longer converges and predictions lose stability. This is where allowance ends and restriction begins, because while cosmology permits variation, it tightly controls how large, how deep, and how connected those variations can be. The cosmological principle works by smoothing the universe, not visually, but statistically, treating individual galaxies as small-scale noise and focusing instead on how matter behaves when averaged across enormous volumes, where random bumps cancel out and only the underlying structure remains. Under this principle, the universe is allowed to be messy up close but orderly from far away, meaning dense regions can exist as long as they are balanced by underdense regions elsewhere, preserving an overall equilibrium. This rule is what allows scientists to draw a straight line through cosmic history, connecting the early universe to the present day without needing to reset the rules for different locations or directions. If the universe violated this principle at large scales, then distance measurements would depend on where you look, expansion rates would vary unpredictably, and large-scale maps would contradict each other in ways that no adjustment could fix. The principle is not optional, because removing it would require rewriting the equations that describe expansion, gravity, and structure growth, which would then fail to match the overwhelming majority of observations that already work. Because of this, cosmology allows small deviations but rejects large ones, tolerates unevenness but rejects dominance, and permits voids only as long as they behave like part of a repeating pattern rather than a singular exception. Under the standard cosmological model, known as lambda CDM, voids are expected outcomes of structure formation, forming naturally as gravity pulls matter into dense regions and leaves behind expanding pockets of lower density. These voids grow over time, stretching as the universe expands, but their growth is limited by initial conditions set in the early universe, conditions that cap how large underdensities can become without violating the smoothness required at large scales. Simulations built on lambda CDM produce many voids of varying sizes, but they follow a predictable distribution, where small voids are common, medium ones are less frequent, and extremely large ones become vanishingly rare. There is a ceiling to this process because voids cannot merge endlessly without disrupting surrounding structure, and they cannot deepen without pulling matter from regions that would then show compensating overdensities. As a result, lambda CDM predicts a maximum scale for voids, beyond which the probability drops sharply, not gradually, because pushing beyond that scale requires initial fluctuations that the early universe did not produce in sufficient strength. This limit is not arbitrary, but emerges from the physics of inflation, gravity, and expansion working together, locking void sizes into a range that has been confirmed across countless simulations and observations. Voids larger than this range are not just unlikely under lambda CDM, but structurally unsupported, meaning the model does not contain a mechanism that can create them naturally without forcing other parts of the universe to behave incorrectly. Statistical rarity versus theoretical impossibility. Cosmology makes a clear distinction between things that are rare and things that are not allowed, because rare events still live inside the rules, while impossible ones demand new rules. A rare structure can exist if the universe simply rolled an extreme outcome, but that outcome must still fit inside the statistical boundaries defined by the model, even if it appears only once in many simulations. Theoretical impossibility begins when a structure requires conditions that the model cannot generate at all, even when pushed to extremes, because the equations no longer permit that outcome without breaking other confirmed results. This distinction matters because rarity can be accepted reluctantly, while impossibility forces confrontation, and cosmology is built to tolerate discomfort only up to the point where consistency collapses. When a structure sits near the edge of what lambda CDM allows, scientists test whether it could be an extreme but valid fluctuation, running simulations with millions of variations to see if anything similar appears naturally. If nothing comparable emerges, the issue shifts from probability to permission, because the model itself has failed to produce the structure even once. At that point, the problem is no longer how unlikely the structure is, but whether the model has the capacity to create it at all. Why randomness cannot explain this structure. Randomness in cosmology does not mean chaos, because fluctuations in the early universe followed well-defined statistical rules, producing patterns that repeat across scales rather than singular anomalies. Random variation can create clusters and voids, but only within the envelope defined by those rules, meaning randomness fills space evenly with extremes rather than concentrating them into a single dominant feature. For randomness to explain an unusually large underdensity, it would need to be balanced by equally extreme overdensities elsewhere, preserving the overall distribution. But no such compensating features appear at the required scale. Randomness also fades with size, because as volumes grow larger, fluctuations average out, making extreme deviations less likely, not more. A structure that grows more pronounced as scale increases moves in the opposite direction of what randomness produces, signaling that something systematic is at work, rather than accidental. Simulations that include randomness naturally generate many voids, but none that match the combination of size and depth seen here without distorting the rest of the universe beyond recognition. Because of this, randomness cannot be stretched to cover the anomaly without also breaking the agreement between the model and the rest of the sky, which remains well behaved. Scale is the point where tolerance ends, because cosmology can forgive many things except violations that persist across distances large enough to define the universe itself. Small anomalies can be dismissed as local effects, measurement issues, or rare events, but large-scale anomalies threaten the assumptions that allow cosmology to function as a science rather than a collection of case studies. When a structure spans a volume so vast that it challenges the idea of uniformity, it becomes a red flag, not because it is dramatic, but because it refuses to blend into the background even when averaged over enormous distances. Scale determines whether a feature belongs to structure formation or to something more fundamental, because only fundamental processes can operate coherently across such distances. Once scale crosses the threshold where averaging no longer smooths the feature away, the anomaly stops being about detail and starts being about framework. This is why size matters more than shape, depth more than contrast, and reach more than appearance, because scale decides whether cosmology can absorb a surprise or must confront a limitation. At that point, the question is no longer whether the structure exists, but whether the rules that describe the universe are complete enough to contain it at all. Once the anomaly could no longer be argued away, the focus shifted from whether it existed to how large it actually was, because in cosmology size is not just a detail, but a verdict, and measuring this structure became the only way to decide whether it belonged inside known limits or outside them. The first measurement was not about distance or mass, but about how much of the sky it occupied, because angular size is the most direct thing a map can show without assumptions. And this region covered an unusually wide span, stretching across many degrees of sky in a way that made it impossible to dismiss as a small local dip or a narrow line of sight effect. Angular size matters because the sky is a dome, and anything that spreads wide across that dome must either be very close or unimaginably large, and this feature was not close, which immediately forced its physical scale upward before any deeper calculations were even made. Measured edge to edge, the region spanned a significant fraction of the visible sky, far larger than typical voids traced in galaxy maps, and large enough that its outline remained visible even when the map resolution was reduced, a sign that the structure was not dependent on fine detail, but dominated at coarse scales. This wide angular footprint meant the anomaly was not confined to a narrow cone or a single direction, but occupied a broad region that could not be erased by adjusting boundaries or masking nearby objects. Once angular size was locked in, the next step was converting that span into physical distance, which required knowing how far away the structure actually sat in space. Estimated physical diameter. Using redshift data to anchor distance, researchers translated the wide patch on the sky into a three-dimensional object, and the result was immediately unsettling, because the diameter reached hundreds of millions of light-years even under conservative estimates, and under less restrictive models, pushed past the billion light-year mark. This was not a small correction or a matter of rounding, because the lower and upper bounds both landed far beyond the scale of ordinary cosmic voids, placing the structure among the largest known features ever associated with missing matter rather than excess matter. The diameter was not measured as a clean sphere, but as an extended region with depth and curvature, meaning different slices of the structure reached different sizes depending on how strictly its edges were defined. But all reasonable definitions agreed on one thing, that it was enormous. Even when boundaries were drawn tightly to avoid exaggeration, the structure remained too large to fit comfortably inside the expected size distribution produced by standard simulations. The sheer diameter mattered because volume grows faster than width, meaning that increasing the size by even a modest factor multiplies the amount of missing matter dramatically, pushing the anomaly from unusual to extreme. At these scales, the structure was no longer comparable to known voids, but instead rivaled the largest superstructures ever mapped, except inverted, defined not by what was there, but by what was missing. Distance was critical, because a nearby structure could appear large while being physically modest, but this region was not nearby, sitting at a distance that placed it firmly within the large-scale structure of the universe, rather than the local cosmic neighbourhood. Measured through galaxy redshifts, the structure lay far beyond local clusters and superclusters, ruling out the possibility that it was a product of local cosmic weather or recent formation. Its distance placed it at a point where the universe was already mature, where structures had long settled into predictable patterns, making the presence of such a deep underdensity harder to reconcile with normal evolution. This distance also meant that light from background sources had travelled through the region for a significant portion of its journey, amplifying any effects the underdensity might have on passing radiation. Because it was not close, parallax and projection effects could not be used to shrink it, locking in its true scale rather than allowing it to collapse into a smaller artifact. The farther away the structure sat, the more serious the measurement became, because distant anomalies reflect conditions shaped early in cosmic history rather than recent local rearrangements. The redshift range of the structure showed that it was not a thin slice, but an extended feature spanning a wide stretch of cosmic distance, meaning it occupied a long segment of space rather than a single moment frozen in time. Galaxies within the affected region shared a consistent redshift range that marked a sustained drop in density rather than a brief dip caused by survey boundaries or selection effects. This continuity across redshift confirmed that the underdensity was not caused by missing data or incomplete coverage, because the same pattern appeared across multiple layers of distance. The structure persisted through redshift slices that normally show independent behavior, indicating that it was coherent across time as well as space. This range also ruled out the idea that the anomaly was tied to a single epoch, because it extended across distances that correspond to different stages of cosmic expansion. A feature that holds together across redshift in this way cannot be reduced to a coincidence of timing or alignment, because it occupies real volume rather than a thin shell. Once size and distance were established, density became the most important measurement, because density determines how strongly a structure influences everything around it. The density contrast measured how much matter was missing compared to the cosmic average, and this contrast was not mild, because the region showed a significant drop well below what is typically seen even in large voids. This was not a gradual thinning, but a sustained underdensity that persisted across the structure's full volume, indicating a genuine shortage of matter rather than a redistribution within the same region. Density contrast matters because the universe is built on balance, and removing matter from one place usually means piling it somewhere else, but no matching overdensity appeared nearby at the required scale. The deeper the contrast, the more difficult it becomes to explain how the structure formed without leaving scars elsewhere in the cosmic web. Measurements showed that the region was not just wide, but deeply depleted, amplifying its impact beyond what width alone would suggest. Width defines how much space the structure occupies, but depth defines how strongly it disrupts the universe, because a shallow void can stretch wide without doing much damage, while a deep one reshapes how matter and light behave across enormous distances. A deep underdensity alters the paths of photons passing through it, changes the growth rate of nearby structures, and leaves signatures that can be detected long after the region itself has formed. Depth also reflects the strength of the initial conditions that created the structure, because carving out a deep void requires stronger deviations early on than simply spreading matter thinly. A wide but shallow region could be dismissed as a gentle fluctuation, but a deep underdensity demands explanation, because it represents a significant departure from average conditions. The measurements showed that the structure combined both width and depth, but it was the depth that pushed it beyond comfort, because deep voids are harder to grow, harder to maintain, and harder to reconcile with uniform expansion. Depth also compounds volume, because removing more matter from the same space multiplies the anomaly's impact, turning size into consequence rather than just scale. This is why measuring the whole was not just about drawing its outline, but about understanding how empty it truly was. Because emptiness at this level carries weight, influence, and implications that cannot be ignored once the numbers are fixed. Calling this structure a void creates a false sense of familiarity, because voids are expected parts of the universe, common outcomes of gravity pulling matter into dense regions and leaving quieter spaces behind. But what appears here does not behave like the voids cosmologists have studied for decades, and that difference is not subtle or semantic, but structural. Normal cosmic voids are numerous and well understood, appearing as bubble-like regions between filaments of galaxies, typically surrounded by walls and clusters that clearly show where the missing matter went, and these voids come in predictable sizes that repeat across simulations and observations with remarkable consistency. Extreme supervoids, by contrast, sit at the far edge of what models can produce, not because they are entirely forbidden, but because they require unusually strong early conditions that are statistically suppressed, meaning they appear rarely and with limited depth, even when simulations are pushed hard. This structure does not fit comfortably into either category, because while it shares the label of underdensity, it exceeds normal voids by scale and pushes beyond what extreme supervoids are expected to reach without tearing balance elsewhere in the cosmic web. Normal voids tend to have clear boundaries where matter piles up, forming bright rims of galaxies that trace where gravity redirected material. But this structure lacks the compensating walls expected for something of its size, leaving an imbalance that does not resolve locally. The absence of these compensating features is one of the first signs that this is not simply a void scaled up, but something that violates the usual give and take between empty regions and dense ones. Normal cosmic voids versus extreme supervoids. Normal voids emerge naturally as gravity amplifies tiny differences in density left behind after the universe's earliest moments, causing matter to flow out of slightly underdense regions and into denser ones, creating expanding bubbles that grow but remain limited by surrounding structure. These voids are common, overlapping and relatively shallow, meaning they remove some matter from a region but leave enough behind that the universe remains balanced when averaged over large scales. Extreme supervoids are rarer, larger and deeper, forming from unusually low initial density regions. But even these follow rules, because their growth slows as surrounding matter resists being drained too far, preventing runaway emptiness. Simulations that generate extreme supervoids still show them embedded within a network of filaments and clusters that compensate for their size, maintaining the overall mass distribution expected under known physics. The structure in question does not follow this pattern cleanly because its size places it beyond typical supervoids, while its surroundings do not show the dense walls or excess clustering required to offset such a large absence. This mismatch creates a problem because scaling up a void should scale up its boundaries as well. Yet here, the boundaries do not match the interior, suggesting the process that shaped it did not follow standard void growth. The seeds of all cosmic structure were planted during inflation, when space expanded rapidly and tiny fluctuations in density were stretched across vast distances, creating regions that were slightly more dense or slightly less dense than average. These early differences were small, but gravity amplified them over time, pulling matter into denser zones and allowing underdense regions to expand and empty out, forming the cosmic web seen today. Under this process, voids are born from places where the initial density dipped just enough to lose the competition for matter, but not so much that they became completely barren. The strength of these early fluctuations follows a well-measured distribution, meaning extremely deep or wide underdensities are strongly suppressed from the start. Because inflation produced fluctuations that were smooth and evenly distributed, voids formed gradually and predictably, with their final sizes reflecting how far those initial conditions could realistically evolve. This framework tightly limits how extreme voids can become, because pushing beyond those limits would require initial conditions that inflation does not generate in sufficient strength or frequency. This structure breaks formation models because its size and depth require an initial underdensity that exceeds what inflation is expected to produce without leaving other visible consequences elsewhere in the universe. To form something this large through normal evolution, matter would have needed to flow outward over enormous distances without piling up in surrounding regions, which contradicts how gravity redistributes mass. Simulations that attempt to reproduce such a structure either fail to generate it at all or create side effects that are not observed, such as overly dense walls or distorted clustering patterns nearby. The problem is not just scale, but coherence, because the structure maintains its underdensity across a wide volume instead of fragmenting into smaller voids, which is what models predict should happen as structures evolve. This persistence suggests a different origin or an influence that standard formation models do not include, because normal voids do not resist fragmentation at these scales. When models are adjusted to allow this structure, they tend to disrupt agreement with the rest of the sky, meaning fixing one problem creates many others. The difference between absence of galaxies and absence of matter. A region with few galaxies does not automatically imply a lack of matter, because galaxies trace only part of the total mass, and dark matter can still dominate even where visible structures are sparse. Many voids contain dark matter filaments and low-mass halos that do not host bright galaxies, meaning galaxy counts alone can exaggerate emptiness. In this case, multiple lines of evidence show that the shortage goes beyond visible galaxies, pointing to a real deficit in total matter rather than a bias in what can be seen. If galaxies were simply missing while matter remained, gravitational effects would still reveal the mass through lensing and clustering, but those signals are reduced as well. This distinction matters because galaxy absence can be explained through feedback and formation efficiency, while matter absence requires a structural explanation tied to the universe's underlying framework. Here, the data indicate that the region lacks both luminous and dark matter in proportions that exceed expectations, confirming that this is not a cosmetic gap, but a physical one. Weak gravitational lensing provides a way to map matter directly, because mass bends light regardless of whether it shines, allowing scientists to detect dark matter through its subtle influence on background galaxies. In regions with normal matter content, background galaxies appear slightly stretched or distorted in consistent ways, revealing the mass distribution along the line of sight. In this region, weak lensing measurements show reduced distortion, indicating a genuine shortage of mass rather than an observational blind spot. This absence appears across the same spatial extent as the galaxy underdensity, tying the two together into a single physical structure. Lensing does not depend on galaxy brightness or type, which removes many sources of bias and strengthens the conclusion that matter itself is missing. The alignment between lensing data and galaxy surveys closes the door on explanations based solely on visibility or sampling, because gravity responds to all mass equally. What remains is a region that is not merely quiet or sparse, but genuinely depleted, making it fundamentally different from ordinary voids that still retain much of their underlying mass. This is why the label void fails here, because voids are empty in appearance, while this structure is empty in substance, and that difference places it outside the comfortable category of features cosmology already knows how to explain. The CMB as the oldest observable light. Long before telescopes started counting galaxies, the universe left behind a faint glow that fills every direction. A glow that comes from a time when there were no stars, no galaxies, and no planets. Only heat and particles moving together as one. And that glow became the first place where something strange quietly appeared. This light is called the cosmic microwave background, and it is the oldest light that can still be observed. Older than any galaxy image, older than any star cluster, older than any structure that gravity later shaped, because it was released when the universe cooled enough for light to finally travel freely through space, carrying with it a snapshot of conditions from that early moment. Unlike light from stars, which comes from specific places, the cosmic microwave background arrives evenly from all directions, wrapping the sky like a shell, which makes it one of the most powerful tools in cosmology, because it does not favour one region over another and does not depend on where galaxies later formed. This background light is extremely cold by everyday standards, just a few degrees above absolute zero, and it is remarkably smooth, which is exactly what scientists expected if the early universe was nearly uniform. But it is not perfectly smooth, and those tiny differences are where the story begins. The cosmic microwave background formed when the universe was still dense and hot, filled with charged particles that scattered light constantly, making space opaque. But as the universe expanded and cooled, those particles combined into neutral atoms, allowing light to finally move freely for the first time. That moment locked in a record of the universe's early conditions, freezing tiny differences in temperature across the sky that reflected slight variations in density, variations that later grew into galaxies, clusters, and voids. Because this light has been travelling ever since, without being replaced or refreshed, it acts like a fossil imprint, preserving information from a time long before any visible structure existed. Every direction we look, the cosmic microwave background comes from roughly the same distance, meaning it provides a full sky view of the early universe, not pieced together from fragments, but seen all at once. This makes it uniquely sensitive to large-scale patterns because small local changes average out, while broad features remain visible even after billions of years of expansion. The background light is not seen with normal cameras, but with instruments designed to detect microwave radiation, converting faint signals into detailed maps of temperature across the entire sky. These maps look calm at first glance, but they carry an enormous amount of information, encoded in variations so small they require precise instruments to detect. The temperature differences in the cosmic microwave background are tiny, measured in millionths of a degree, but they are not random noise because their pattern reflects the distribution of matter and energy at the time the light was released. Hotter regions correspond to slightly denser areas where gravity held on to energy, while cooler regions mark places where matter was slightly less dense, allowing photons to lose energy as they climbed out of shallow gravitational wells. These fluctuations follow statistical rules that can be predicted and tested, meaning scientists know what kinds of patterns should appear if the universe behaved according to known physics. When these patterns are analysed, most of the sky matches expectations extremely well, reinforcing confidence in the underlying model that describes how the universe evolved from its earliest moments. Because the background light comes from such an early time, any large or unusual feature seen in it cannot be blamed on later processes like star formation or galaxy mergers, which makes anomalies especially important. Temperature maps of the cosmic microwave background are not just pictures, but data sets that can be measured, filtered, and tested repeatedly, allowing scientists to calculate how likely certain features are to appear by chance. This statistical power is what turns a faint patch of cooler light into a serious clue rather than a visual curiosity. Discovery of the cold spot. The cold spot first appeared in full sky maps created to study the cosmic microwave background, emerging as a large region noticeably cooler than its surroundings. Not dramatically cold in absolute terms, but cold enough compared to nearby areas to stand out once the data was processed. It did not announce itself immediately because early maps contain many small cold and hot regions. But as analysis improved and noise was reduced, this region remained prominent while others blended into the background. What made it striking was not just that it was cold, but that it was smooth and extended, lacking the small-scale texture seen elsewhere in the map. As researchers applied different filters and analysis methods, the cold spot continued to appear, resisting attempts to explain it away as an artifact of data handling or foreground contamination. Its persistence across multiple analyses turned it from an oddity into a feature that demanded explanation, because removing it required assumptions that conflicted with how the rest of the map behaved. The cold spot was not discovered by staring at the sky, but by letting the data speak, revealing a feature that stood out statistically rather than visually at first glance. The cold spot occupies a specific region of the sky, located in the southern hemisphere of the cosmic microwave background map, far from the plane of our galaxy, which reduces the chance that it is caused by interference from nearby stars or dust. Its position is well defined in celestial coordinates, allowing it to be studied repeatedly with different instruments and analysis techniques, each time returning to the same patch of sky. In terms of angular size, the cold spot spans several degrees across, making it much larger than typical temperature fluctuations, which usually appear as small patches scattered across the map. This size places it in a category of features that probe large-scale structure rather than small local variations, because only processes operating across vast distances can create such extended patterns. The cold spot is not a sharp circle, but a broad area with a gradual temperature drop toward its center, which distinguishes it from noise or point source interference. Its scale alone made it unusual because larger features are statistically suppressed in standard models, meaning they should appear rarely and with less contrast than smaller ones. The cold spot stood out, not because it was the coldest point on the map, but because of its combination of size, depth, and smoothness, which together made it unlikely under the expected distribution of fluctuations. Statistical tests applied to the map showed that while small cold regions are common, large coherent ones are not, especially when they extend across several degrees without breaking into smaller patches. When researchers measured how often a feature like this should appear in simulated maps built from known physics, the answer was uncomfortable, because such a feature appeared far less frequently than expected if the universe followed standard rules everywhere. Different statistical approaches were used to test the anomaly, including wavelet analysis and angular power measurements, and the cold spot continued to appear as an outlier across methods. Its significance did not vanish when data improved, which is often what happens when apparent anomalies are driven by noise or limited resolution. The cold spot also did not align with known sources of contamination, such as foreground emissions or instrumental effects, which were carefully modelled and subtracted. Because it appeared in the cleanest regions of the sky and survived multiple rounds of analysis, the cold spot earned its reputation not as a glitch, but as a genuine feature of the cosmic microwave background. This made it the first serious hint that something unusual might exist along that line of sight, long before galaxy maps would reveal anything missing at all, placing the cold spot at the beginning of a mystery that would only deepen as more data arrived. The reason the cold spot caused so much unease is not because cold regions are forbidden, but because the universe was never supposed to make one like this, not this large, not this smooth, and not this rare, according to the rules that explain nearly everything else we see in the cosmic microwave background. Those rules are built on the idea that the early universe had tiny differences in density that followed a very specific pattern, a pattern that behaves like random noise but with limits, meaning fluctuations happen freely but only within a narrow range. This is where the problem begins, because the cold spot sits far outside that expected range, not as a small outlier, but as a feature that pushes against the edges of what the model allows. Gaussian fluctuations and probability. The temperature variations in the cosmic microwave background are expected to follow what is called a Gaussian distribution, which means most fluctuations are small, medium ones are less common, and extreme ones are very rare. This kind of distribution is not guessed. It comes directly from how inflation is thought to have stretched tiny quantum ripples across the universe, smoothing them out while keeping their randomness intact. In a Gaussian universe, extreme events can happen, but they come with clear probabilities, and those probabilities drop fast as size and strength increase. Small cold spots appear everywhere, and nobody worries about them, because they fit neatly into the expected curve. The cold spot does not fit neatly anywhere on that curve. Its size alone already pushes it toward the tail of the distribution, and its depth pushes it even further. But when both are combined, the odds shrink dramatically. Simulations based on Gaussian fluctuations were run again and again, producing full sky maps that looked almost exactly like the real universe, except they almost never produced a cold spot with the same shape and scale. When they did appear, they were usually weaker, smaller, or broken into fragments, not smooth and continuous like the real one. This mismatch between prediction and observation is what turns a rare event into a problem, because probability is not about whether something can happen once, but whether it should happen at all, given enough trials. Once the cold spot was identified as unusual, the discussion shifted toward how unusual it really was, because in science, rarity needs to be measured carefully. Researchers began calculating its statistical significance, which is a way of asking how often a feature like this would appear if nothing strange were going on. Depending on how the analysis was done, the cold spot landed at significance levels that range from mildly surprising to deeply uncomfortable. Some approaches suggested it was unlikely, but not impossible, while others placed it far enough into the tail of the distribution to raise serious doubts about pure chance. This led to debates about confidence levels, because the sky is large, and when you search long enough, rare features are bound to appear somewhere. The key issue was not whether a rare fluctuation could exist, but whether this particular one crossed the line from rare to implausible. Different statistical tools were applied to avoid bias, testing whether the cold spot remained significant when measured in different ways. What made the debate difficult was that the cold spot did not disappear under scrutiny. It weakened slightly in some analyses, but strengthened in others. No single method could dismiss it cleanly, which kept it suspended in an uncomfortable middle ground, too strange to ignore and too solid to discard. Why foreground contamination was ruled out. One of the first attempts to explain away the cold spot was to blame something closer to home, because signals from within our galaxy can interfere with cosmic measurements. Dust, gas, and charged particles in the Milky Way emit radiation that can distort temperature maps if not properly removed. The cold spot's location worked against this explanation, because it sits far from the galactic plane, where interference is weakest and cleaning methods are most reliable. Maps were created at different frequencies because foreground sources behave differently depending on wavelength, while the cosmic microwave background stays consistent. If the cold spot were caused by foreground contamination, it would change or fade when viewed at different frequencies. It did not. The feature remained stable across frequency bands, matching the behavior expected from true background radiation rather than local interference. Additional masking and subtraction techniques were applied, removing known sources of contamination with increasing precision. Each time the foregrounds were stripped away, the cold spot remained behind, unchanged in shape and position. This made the contamination explanation increasingly difficult to defend, because removing the supposed cause did not remove the effect. The final blow to simple explanations came when different instruments using different designs and different observation strategies all detected the same feature. These instruments did not share the same system noise, calibration errors, or scanning patterns, which means shared flaws were unlikely. Each dataset was processed independently, often by separate teams, yet the cold spot appeared in the same region of the sky with the same basic properties. This consistency matters because random errors do not repeat themselves cleanly across independent measurements. Instrument-specific glitches tend to move, distort, or vanish when viewed through a different system. The cold spot did none of these things. Its temperature profile, size, and smoothness stayed consistent, even as resolution improved and noise levels dropped. As data quality increased, the surrounding fluctuations sharpened, but the cold spot itself remained broad and coherent. This ruled out the possibility that it was a leftover artifact from early instruments or crude data processing. What remained was a feature that behaved exactly like a genuine imprint on the cosmic microwave background, but one that refused to fit comfortably within the rules that were supposed to produce that background. At that point, the question was no longer whether the cold spot was real, but what kind of structure could leave such a mark on the oldest light in the universe. The connection between the cold spot and the missing matter seen in galaxy maps begins with light, because light carries information not just about where it came from, but also about every region it travels through. Photons from the cosmic microwave background journey across billions of light years, passing through clusters, filaments, and voids along the way. Every structure they encounter leaves a subtle imprint on their energy, bending their path slightly or changing their temperature by a tiny amount. This effect is invisible to the eye, but with precise maps it can be measured, and it provides a way to link the cold spot to a real structure in space rather than leaving it as an unexplained anomaly. The integrated Sachs-Wolf effect. Explained visually. Imagine a photon moving through a valley in a hilly landscape. The valley represents a region where matter is sparse, an underdensity. As the photon falls into the valley, it gains energy from the gravitational pull, accelerating slightly as it descends. When it climbs back out, it should lose the same amount of energy, coming out just as it went in. In a perfectly static universe, these gains and losses cancel completely. But the universe is not static, it is expanding. As the photon crosses the valley itself stretches, becoming shallower as the photon climbs out. That means it loses less energy climbing out than it gained falling in, and the photon emerges slightly cooler than it would have otherwise. This subtle change in temperature is called the integrated Sachs-Wolf effect, or ISW effect for short. It only occurs on large scales where cosmic expansion and gravitational potentials interact over billions of light years. Regions that are underdense, like supervoids, produce cold imprints, while overdense regions, like superclusters, produce hot imprints. The effect is cumulative, visible only when photons traverse enormous stretches of space, and it is measurable by comparing cosmic microwave background maps to large-scale galaxy surveys. As photons enter a low-density region, they feel a small gravitational pull, accelerating slightly as they descend into the underdensity. The key is that the universe's expansion is stretching space during the photon's journey. By the time the photon climbs out, the potential well has flattened, so it loses less energy than it gained. The result is a net loss of energy, which appears as a colder temperature when mapped in the cosmic microwave background. This process depends on the size and depth of the underdensity. Small voids produce tiny temperature drops, almost impossible to detect. Larger voids, hundreds of millions of light years across, produce stronger signals. The energy loss is subtle, often measured in millionths of a degree, but over the enormous scales of supervoids, the effect becomes observable. Photons act like messengers, carrying evidence of the structures they traverse. If a region is unusually empty and large enough, it should leave a measurable imprint on the oldest light in the universe. This is the exact prediction that links the cold spot to a potential missing matter structure. Predictions versus observed temperature drop. When cosmologists calculated how much the cold spot should cool from a standard supervoid, they predicted a drop in temperature based on the size, depth, and distance of the void. Using the known properties of gravity, expansion, and photon travel, the numbers suggested only a small, subtle cold patch. Observations confirmed a cold spot, but its temperature drop was far larger than what any normal void could produce. Simulations using typical supervoids produced temperature dips that were far weaker than the cold spot. Even extreme supervoids, at the very edge of plausible sizes, fell short of the observed drop. The discrepancy was not minor. The measured temperature change was several times larger than predicted. The difference was clear. Something about the region along that line of sight was not behaving like any structure accounted for in standard cosmology. Photons passing through the expected underdensity could explain some of the cold spot, but not the entire magnitude of its coldness. The cold spot is too cold even when a supervoid is considered, because the depth and scale of the observed temperature drop exceed what the integrated Sachs-Wolf effect can produce under normal conditions. To reach the observed cooling, the void would need to be extraordinarily large and deep, far beyond what simulations or inflationary fluctuations predict. Standard cosmology limits void sizes, because creating a void much larger than hundreds of millions of light years either requires an impossible initial underdensity or produces distortions in the surrounding universe that are not observed. The cold spot ignores those limits. It acts as if the universe allowed an extreme structure that should be statistically impossible, one that removes far more gravitational influence than any normal void can. No combination of void depth, size, or distance produces a drop as large as the cold spot. The observed temperature exceeds every standard scenario by a significant margin. This discrepancy signals that the structure responsible, if it exists, is not ordinary. It cannot be a regular void, because regular voids follow rules dictated by inflation, gravity, and cosmic expansion. Faced with this mismatch, researchers began to consider that the cold spot might point to a structure unlike anything previously observed, a supervoid that is extreme in both scale and depth, not merely at the tail of a distribution, but beyond the boundaries allowed by standard formation models. The correlation between the cold spot and the underdensity detected in galaxy surveys gave the first tangible clue. The missing matter responsible for the cold spot is not just a local effect, not just a coincidence, and not just an observational artifact. It appears to be a massive, coherent structure spanning hundreds of millions of light years, capable of influencing photons from the early universe in a measurable way. This realization transformed the cold spot from a statistical curiosity into a hint of something real in the cosmic web, a physical structure that challenges existing understanding. The photons arriving cold are now understood not as random noise, but as a sign that something extraordinary exists along that line of sight, something far larger and emptier than ordinary cosmic voids, and something that cannot be explained by normal rules of cosmic structure formation. The cold spot was only the beginning. Light from the early universe suggested something unusual, but to see the structure directly, astronomers turned to galaxies. Galaxies act as traces of matter, and by mapping them in detail, researchers could see not just the absence of light, but the absence of mass itself. Multiple surveys combined to provide the first clear three-dimensional picture of the missing matter, transforming speculation into measurable structure. The surveys that changed everything. The Sloan Digital Sky Survey, or SDSS, was one of the first to provide a high-resolution map of the nearby universe, covering millions of galaxies across vast portions of the sky. By cataloguing galaxy positions and measuring redshifts, SDSS gave cosmologists the ability to see large-scale structure directly. When researchers focused on the area aligned with the cold spot, they noticed a striking underdensity, a patch of space with far fewer galaxies than surrounding regions. The Dark Energy Survey, DES, pushed the mapping further. Using deeper imaging in optical and near-infrared light, DES observed fainter galaxies at greater distances, filling in gaps left by earlier surveys. This allowed scientists to confirm that the underdensity seen in SDSS was not a local anomaly, but extended across hundreds of millions of light years, reaching distances where the universe had long settled into its large-scale structure. WISE-2 MASS surveys added another layer of data. These infrared surveys traced older stars and dust-obscured galaxies, allowing regions that optical surveys might miss to be studied. The combination of WISE-2 MASS with SDSS and DES provided a multi-wavelength view, ensuring that the observed underdensity was not an artifact of one type of observation. Every dataset pointed to the same unusual feature in the same place in the sky, creating a consensus among independent instruments. Mapping the region across multiple wavelengths also revealed the consistency of the void. Optical surveys captured luminous galaxies. Infrared surveys revealed hidden galaxies, and all showed the same deficit. This cross-survey agreement strengthened the case that the structure is real, not an error or a bias, and it confirmed that the cold spot line of sight corresponds to an actual underdense region in the universe. Three-dimensional mapping of the whole. Seeing the underdensity in 2 dimensions was only the first step. Galaxies exist in 3-dimensional space, and understanding the structure required translating redshift into physical distance. Redshift measures how much the light from a galaxy has been stretched by the expansion of the universe, which can be converted into a distance along the line of sight. By combining redshifts with angular positions, astronomers could reconstruct the void in 3 dimensions, tracing its true shape and size. The 3D maps revealed that the structure is enormous, stretching across hundreds of millions of light years, and that its shape is not a simple sphere. Instead, it appears elongated, with its length along the line of sight potentially greater than its width across the sky. This elongation complicates interpretations because elongated voids produce a stronger effect on passing photons than spherical ones of the same volume, which may help explain part of the cold spot's extreme temperature drop, but does not solve the problem entirely. Evidence also suggests the void may have a layered structure. Instead of a single uniform underdensity, the region may consist of multiple overlapping subvoids, each with its own depth and slightly different distance. This layered composition adds complexity, because photons passing through such a region would experience a cumulative effect, not a simple ISW signal from a single void. The geometry of the structure worsens the problem for cosmologists. Simulations show that voids of this size and elongation are exceedingly rare, and forming multiple aligned subvoids along the same line of sight is statistically unlikely under standard cosmological models. The more detailed the map becomes, the clearer it is that this is not a normal void, but a massive, structured anomaly stretching across an extraordinary volume of space. By combining multiple surveys, measuring galaxies across wavelengths, and reconstructing the void in 3 dimensions, researchers moved from detecting a statistical anomaly in the cosmic microwave background to confirming a real, tangible structure that matches the cold spot's line of sight, a feature so large and unusual that it challenges the limits of our understanding of the universe. The Eridanus Supervoid. The structure responsible for the cold spot finally received a name, the Eridanus Supervoid. Its name comes from the constellation Eridanus, where the feature is projected on the sky, giving astronomers a clear reference point for the massive underdensity that stretches across hundreds of millions of light years. Associating it directly with the cold spot was natural, because the underdensity aligns almost perfectly with the line of sight where the cold spot's photons originate. This connection turns what was once a statistical curiosity in the cosmic microwave background into a real, 3-dimensional cosmic structure that can be studied directly. Size estimates for the Eridanus Supervoid vary depending on the method and model used, but even the most conservative measurements place it at hundreds of millions of light years across, while some reconstructions push its length past 1 billion light years. Its shape is elongated along the line of sight, potentially layered, which increases the cumulative effect on photons traveling through it. And the deeper the underdensity, the stronger the imprint it leaves on the cosmic microwave background. Density estimates show a significant deficit of matter compared to the cosmic average, with uncertainties arising from survey depth, selection effects, and assumptions about galaxy mass correspondence. Even accounting for these uncertainties, the void is empty enough that photons passing through lose measurable energy, producing the cold spot. Conservative estimates still place the underdensity near the limits of what the standard model of cosmology, lambda CDM, can tolerate. The void's combination of size, depth, and coherence is not only unusual, but stretches the boundaries of the physical laws that generate large-scale structure under normal inflationary conditions. The discovery of the Eridanus Supervoid sparked a theoretical scramble. How could a structure this large and deep exist without breaking everything we know about the universe? Cosmologists immediately tried to fit it into the lambda CDM framework, which has been remarkably successful at explaining the growth of structure from the smooth fluctuations left by inflation. The first approach was to treat the void as extreme but allowed. In theory, if the initial density fluctuations were unusually low along this line of sight, such a void could form, even if it was improbable. Simulations were run using extreme initial conditions, pushing parameters to the edge of what lambda CDM allows, and in some cases a structure approaching the Eridanus Supervoid could appear. But these simulations almost always failed in critical ways. Either the void formed too late, or its shape was wrong, or the surrounding regions became unrealistically overdense to compensate. Producing a void this deep and elongated while leaving the rest of the universe unaffected proved far more difficult than initial probability calculations suggested. The problem is one of fine-tuning. To match observations, initial conditions must be carefully selected, a very specific underdensity in just the right place, with just the right depth and shape, without causing other contradictions elsewhere in the cosmic web. Nature does not appear to handcraft such perfect conditions, which is why rare but allowed is no longer satisfying as an explanation. A statistical outlier should appear occasionally, but when the feature has such a large impact and a coherent structure, calling it rare begins to feel like an ad hoc defense. The fine-tuning problem is compounded by the void's alignment with the cold spot. It is not enough for a supervoid to exist somewhere. It must exist precisely along the line of sight of the cold spot in the cosmic microwave background. Random alignment is improbable, and the combination of size, depth, and position puts the Eridanus Supervoid at odds with the expectations of standard cosmology. Even extreme simulations struggle to reproduce it. They either underpredict the temperature imprint on the cosmic microwave background, overcompensate with surrounding structures, or fail to create an elongated, coherent shape across hundreds of millions of light years. Every attempt highlights the limits of lambda CDM in accommodating such a structure naturally, showing that while the model survives, it is forced into uncomfortable parameter choices that strain credibility. Theoretical damage control has thus become a central focus of modern cosmology. Researchers must decide whether the Eridanus Supervoid is a statistical fluke, an undiscovered mechanism within standard physics, or a sign that our understanding of large-scale structure formation requires revision. The issue is no longer about whether the void exists, it clearly does, but about how it can exist without violating the rules that have otherwise successfully explained the universe for decades. You see, inflation is responsible for seeding the large-scale structure we observe today, turning tiny quantum fluctuations into the blueprint for galaxies, clusters, filaments, and voids. These initial ripples dictated how matter would clump over billions of years, producing the cosmic web. Inflation also predicts homogeneity at very large scales. While small fluctuations exist, the universe should appear roughly uniform when averaged across hundreds of millions of light years. Extreme departures from this uniformity are unlikely, because inflation smooths space while imprinting only small, random deviations. The Eridanus Supervoid pushes beyond these expectations, representing a coherent underdensity on a scale that inflationary models struggle to accommodate. Some theorists have tried to explain the supervoid as a rare inflationary anomaly. Perhaps a fluctuation during inflation was unusually deep, leaving behind a region with less matter than the surrounding universe. In principle, this could produce a void large enough to impact the cosmic microwave background. However, creating such a fluctuation requires an improbably precise set of initial conditions. These inflationary anomalies introduce new problems elsewhere. A fluctuation deep enough to create the supervoid would likely distort the rest of the universe's structure, producing other extreme over- or underdensities that are not observed. The universe would no longer match the smooth statistical patterns seen across most of the sky. Attempts to tweak inflation to allow one massive anomaly often break agreement with the cosmic microwave background's small-scale fluctuations or the observed distribution of galaxies. To accommodate the Eridanus Supervoid, inflation models would need significant changes. They might require non-standard fields, unusual dynamics during expansion, or mechanisms to isolate a single extreme underdensity without affecting surrounding region. Each of these adjustments moves away from the simplicity and predictive power that makes inflation successful, creating tension between explaining one anomaly and preserving the overall framework. Dark energy and expansion effects. Another avenue for explaining the void involves accelerated expansion. Dark energy drives the universe to expand faster over time, and this expansion could, in theory, enhance the growth of underdense regions. As space stretches, low-density areas could become emptier, potentially deepening voids over billions of years. Time-dependent dark energy models allow the expansion rate to vary with cosmic time, opening the possibility that voids might grow faster than in standard lambda CDM. Some models suggest that if dark energy increased or decreased in specific ways, it could exaggerate existing underdensities, making a void like the Eridanus Supervoid more extreme than simple gravity would predict. However, observational constraints limit this explanation. Supernova surveys which track how light from exploding stars dims over vast distances, provide precise measurements of cosmic expansion. Baryon acoustic oscillation data, which measures the imprint of primordial sound waves on galaxy distributions, further constrains how expansion can evolve. Both sets of data tightly restrict the range of allowed dark energy behavior. Introducing a dark energy effect strong enough to produce the Eridanus Supervoid would conflict with these observations. Supernova brightness and BAO measurements would indicate a different expansion history than what is actually observed. Any model that amplifies voids significantly risks breaking agreement with the carefully measured growth of structure elsewhere. This creates a tension between theory and observation. Dark energy could, in principle, deepen voids, but the universe does not allow arbitrary acceleration. Observations impose strict limits, leaving little room for expansion alone to explain the cold spot and the Eridanus Supervoid. This makes the supervoid a challenge not just for inflation, but for our understanding of dark energy and how it interacts with cosmic structure over billions of light years. Imagine the universe not as a single balloon, but as one bubble among countless others, each expanding in a frothy, inflating multiverse. This is the idea of eternal inflation. Inflation never truly stops everywhere. Some regions keep inflating, producing new bubble universes, each with its own properties, laws, and structure. Within this endless cosmic foam, our universe is just one bubble floating in an infinite sea. If two bubbles collided during their formation, the impact would leave a mark. Not a mark in paint or debris, but a subtle imprint on the oldest light in the universe, the cosmic microwave background. Photons traveling toward us from the edge of our bubble would carry the signature of that collision. It would appear as a large-scale anomaly, a region slightly hotter or colder than expected, shaped by the dynamics of the collision and the properties of the neighboring bubble. Cosmologists have tried to calculate what such a collision would look like. The predictions are precise in concept, if messy in practice. A bubble collision would produce a disc-shaped feature in the cosmic microwave background, often with a gradient across its surface, where temperature changes gradually from the center outward. The size would be enormous, spanning hundreds of millions of light years, potentially leaving a smooth, coherent cold or hot spot in the sky. The cold spot in the southern hemisphere partially fits this description. Its size and smoothness resemble the predicted imprint of a bubble collision, and its location is consistent with the kind of large-scale feature that such an event might create. Unlike random small fluctuations, the cold spot is unusually coherent across a broad area, which aligns with what a collision model would produce. Its alignment with the Eridanus Supervoid only strengthens the mystery, because a bubble collision could potentially create both a deficit in matter and a corresponding cold region in the cosmic microwave background. However, the evidence is incomplete. The cold spot does not perfectly match all the predicted features of a bubble collision. The temperature gradient is not as pronounced as some models suggest, and other expected signatures like specific polarization patterns or concentric rings are weak or absent. Observations across different frequencies and instruments confirm the cold spot's existence, but they cannot definitively tie it to a bubble collision. The universe may have left hints of a contact with another bubble, or it may simply have produced an extraordinary supervoid. The challenge is that the cold spot sits at the intersection of the improbable and the unexplained, a region large enough to push the limits of known physics, yet subtle enough to evade full confirmation. It teases the idea of a multiverse without offering a smoking gun, making it one of the most intriguing puzzles in modern cosmology. A bubble collision would not just explain the cold spot, it would rewrite the story of the cosmos. It would suggest that our universe is part of a far larger, dynamic structure, that other universes exist beyond what we can see, and that remnants of those encounters are hidden in the faint glow of the cosmic microwave background. The idea is breathtaking, terrifying, and tantalizingly plausible. But for now, it remains a shadow on the map of the universe, waiting for the next piece of evidence to decide whether it is real or a trick of cosmic chance. Non-Gaussian initial conditions. The universe we see today began as tiny fluctuations in the density of matter, ripples so small they could not be detected with the naked eye. In standard cosmology, these fluctuations are assumed to be Gaussian. That means they follow a simple statistical pattern, where small deviations from the average are common, medium deviations are less common, and extreme deviations are extremely rare. Everything from galaxy clusters to cosmic filaments arises from these tiny, random fluctuations stretched across space during inflation, creating a universe that is predictable at large scales, smooth but dotted with small imperfections. Non-Gaussianity is when those early fluctuations break that pattern. Instead of following the neat bell curve of probabilities, some regions might have larger or smaller deviations than expected, in a way that is correlated across space, rather than purely random. In other words, certain parts of the universe would start out special, with more extreme over- or underdensities than Gaussian statistics would allow. Non-Gaussian fluctuations can reshape how cosmic structures form, producing regions that are dramatically emptier or denser than the rest of the universe in a way that standard models cannot naturally explain. If the early universe had significant non-Gaussianity, the rules that govern structure formation would change. Normally, voids like the Eridanus Supervoid are limited in size and depth because the initial fluctuations are small and statistically constrained. Large coherent underdensities are improbable, and the growth of structures elsewhere in the universe is tightly linked to these probabilities. Non-Gaussian initial conditions would allow for more extreme structures. A void could be unusually large or deep without breaking the overall statistics of the universe, because the initial distribution of matter was not evenly random. It opens the door to structures that appear impossible under standard Gaussian assumptions. However, the universe is not entirely permissive. Observations of the cosmic microwave background, particularly from the Planck satellite, provide the tightest constraints on non-Gaussianity. Planck mapped the temperature of the early universe with incredible precision, measuring millions of points across the sky and detecting tiny fluctuations. Any significant non-Gaussianity would produce distinct patterns in these temperature maps, deviations that Planck could detect with high sensitivity. Planck's results show that the universe is remarkably Gaussian. The observed deviations from Gaussianity are tiny, barely measurable, and consistent with random noise. This means that extreme anomalies in the early density field are not allowed in any significant way, and the universe is overwhelmingly consistent with standard inflationary predictions. The statistical rules that govern the formation of galaxies, clusters, and voids are tight, leaving very little room for large outliers. The Eridanus Supervoid pushes hard against these limits. Its size, depth, and alignment with the cold spot suggest a deviation from what Gaussian statistics would predict. If it were produced by non-Gaussian initial conditions, the magnitude of non-Gaussianity would need to be far beyond Planck's constraints. The universe would have had to start with a highly atypical fluctuation, one that produced a massive coherent underdensity without violating the smoothness observed elsewhere. This is not a trivial problem. Non-Gaussian fluctuation sufficient to create the supervoid would leave fingerprints in other places, producing over- or underdensities that Planck would have detected. Yet the rest of the cosmic microwave background remains orderly, matching predictions almost perfectly. The Eridanus Supervoid stands out as an extreme feature, unlike anything else in the observable universe. It behaves as though the early universe allowed one extraordinary event, a massive departure from the Gaussian pattern, while leaving everything else untouched. Attempts to reconcile the supervoid with non-Gaussian initial conditions face a balancing act. The initial fluctuation must be large enough to produce the observed underdensity, extended enough to affect photons passing through billions of light years, and yet isolated enough not to disturb surrounding regions or conflict with galaxy distributions elsewhere. This creates a tension that standard cosmology struggles to resolve. Non-Gaussianity provides a theoretical escape hatch, but it comes with costs. The magnitude required to produce the Eridanus Supervoid challenges the simplest inflation models, forcing theorists to consider exotic scenarios where rare, isolated fluctuations occur without breaking the overall Gaussian nature of the universe. Some models propose mechanisms where certain regions are seeded with extreme underdensities during inflation, while the rest remain nearly Gaussian. Others invoke interactions between multiple fields during inflation to produce localized anomalies. The universe has a way of hiding its secrets in the rarest events, and the Eridanus Supervoid may be one such event. It teases the idea that while most of the cosmos obeys Gaussian rules perfectly, a single, extraordinary fluctuation could leave an imprint powerful enough to produce the cold spot and the massive missing matter along that line of sight. This possibility stretches the imagination and strains theoretical models, because the universe has not left any other evidence of similarly extreme events at comparable scales. Every photon passing through the supervoid carries the story of these initial conditions, the faint imprint of matter that never formed, stretched across hundreds of millions of light years. The cold spot in the cosmic microwave background, aligned perfectly with this empty region, acts as a cosmic fingerprint, suggesting that whatever produced this void was not a simple, random fluctuation, but something more unusual, something that almost feels like the universe bent the rules in one corner while obeying them everywhere else. Non-Gaussian initial conditions remain one of the few viable explanations for the supervoid's existence, but they raise profound questions about the limits of inflation, the origin of cosmic structure, and the extraordinary degree to which the universe is ordered. If the Eridanus Supervoid is a relic of non-Gaussianity, it is the ultimate outlier, a single anomaly in an otherwise perfectly Gaussian cosmos, and its existence forces a rethinking of what is possible during the universe's earliest moments. This void is a reminder that the cosmos is not just a predictable expanse of matter and energy, but a place where rare, almost impossible events can leave traces billions of years later. Non-Gaussianity may be rare, but the supervoid demonstrates that even the rarest of events can dominate a region of space, shaping the light we see today and challenging the limits of the laws that shape the universe from the beginning. The tension is not only theoretical, but observational. Every attempt to reconcile the Eridanus supervoid with Gaussian initial conditions fails to reproduce its size, depth, and coherence simultaneously. Introducing non-Gaussian fluctuations could solve the problem, but the scale of deviation required pushes against the strongest observational constraints we have. The universe allows only tiny deviations from Gaussianity. Yet here is a region that appears to require a colossal one. This forces a confrontation with the very assumptions of cosmology. If one extreme fluctuation can exist, can others exist undetected? Is the supervoid a unique cosmic accident, or a sign that our models of inflation need revision? Non-Gaussian initial conditions provide a framework, but one that is forced to its limits, bending theory in ways that stretch our understanding of the early universe and the processes that built the cosmic web we see today. The Eridanus supervoid may be the smoking gun of non-Gaussianity, the first observable hint that the early universe was not perfectly uniform in its statistical rules. Every photon from the cold spot carries that hint, tracing a path across a region of space where matter was never dense enough to form galaxies, and where the imprint of initial conditions is still visible billions of years after inflation ended. This single, massive underdensity challenges assumptions, reshapes expectations, and highlights the fragile balance of order and chance in the cosmos. Non-Gaussianity, in theory, can explain it, but the magnitude required makes it extraordinary. It is a cosmic oddity, a single feature that simultaneously obeys and defies the rules, a testament to the strange and extreme possibilities hidden within the universe's earliest moments. Gravity is the engine behind the universe's grand architecture. From the tiniest clumps of matter to sprawling galaxy clusters, every filament, sheet, and void owes its existence to gravity. After inflation seeded tiny differences in density, gravity amplified those ripples over billions of years, pulling matter into galaxies and clusters while leaving vast empty regions behind. It's gravity that sculpts the cosmic web, turning randomness into structure, and it is through gravity that voids like the Eridanus Supervoid can emerge, but only up to a point. Modified gravity. The standard picture relies on Einstein's general relativity combined with dark matter to explain how structures grow. Overdense regions collapse under their own pull, while underdense regions expand relative to their surroundings, creating the familiar pattern of clusters and voids. The equations predict the sizes, shapes, and depths of voids, and simulations match observations across nearly the entire observable universe. But the Eridanus Supervoid sits outside those predictions, a void so large and deep that normal gravity, acting on standard dark matter distributions, struggles to explain it. This is where ideas of modified gravity enter the conversation. For decades, astronomers have toyed with the notion that gravity might behave differently on very large scales. MOND, modified Newtonian dynamics, is one approach developed to explain galaxy rotation curves without invoking dark matter. On galactic scales, MOND successfully reproduces the speeds of stars orbiting the outskirts of galaxies. The question becomes, what if gravity also behaves differently on the scale of hundreds of millions of light years? Could an alternative gravitational law make voids grow larger and emptier than expected under general relativity? Most attempts to extend MOND-like ideas to cosmological scales run into problems. Observations of the cosmic microwave background, baryon acoustic oscillations, and supernovae tightly constrain how gravity can act across vast distances. Any model that significantly amplifies void growth risks disrupting the overall balance of the universe. Galaxies would form too quickly in some regions, expansion histories would conflict with supernova data, and the pattern of cosmic microwave background fluctuations would no longer match observations. Essentially, most modified gravity models fail when tested against the precision data that describe the universe at large scales. Yet the Eridanus Supervoid tempts theorists. It is a cosmic anomaly that seems to demand something beyond standard physics. Gravity governs how matter flows into overdensities and evacuates underdensities. And if the void is larger or emptier than general relativity predicts, it raises the question of whether gravity could behave differently under extreme conditions. The supervoid is not just an unusual feature, it is a scale where alternative gravity models could, in principle, reveal themselves. It teases the possibility that our understanding of gravity may be incomplete when applied to the larger structures in the universe. Modified gravity scenarios for the supervoid do not require throwing out general relativity entirely. Some proposals suggest slight tweaks to how gravity operates over tens or hundreds of millions of light years, changes so subtle that they would leave galaxies and clusters mostly unaffected, but allow enormous voids to form more easily. Others propose dynamic gravity laws that vary with environment or density, making underdense regions expand faster than expected without disrupting overdense ones. These ideas are speculative, but offer a pathway to explain a feature that is otherwise nearly impossible to reproduce in standard simulations. The Eridanus Supervoid acts like a natural laboratory for testing these concepts. Its extreme emptiness and coherence amplify the effects of any deviation from standard gravity. If gravity is slightly stronger or weaker over these scales, the imprint would be observable in the cosmic microwave background, galaxy distributions, and weak lensing measurements. Every photon passing through the void, every galaxy that should have formed but did not, becomes a clue about how gravity might operate beyond what we currently know. The tension between standard gravity and the supervoid's properties is subtle but profound. Ordinary gravitational collapse cannot evacuate enough matter to produce the observed deficit across such a massive region without overproducing structures nearby. A modified gravity model could, in principle, selectively accelerate the growth of voids, creating conditions that more naturally match observations. Yet these models must thread a narrow path, respecting the extraordinary agreement between standard theory and the rest of the universe, while explaining this one extreme outlier. The allure of new gravity models is that they offer a way to reconcile the impossible with the observed. The supervoid challenges the assumption that general relativity and dark matter alone can account for all cosmic structures. It hints that the universe may harbour behaviours hidden at extreme scales, where the rules bend subtly but profoundly, creating anomalies like the cold spot and the missing matter behind it. At the same time, these ideas are dangerous territory. Gravity is fundamental. Altering it risks unravelling the delicate cosmic web that exists everywhere else. Yet the Eridanus Supervoid persists, a glaring void that refuses to obey the limits imposed by standard physics. It calls out for creative thinking, for daring ideas that push beyond the familiar framework, while demanding that any proposed modification remain consistent with the rest of the cosmos. In exploring modified gravity, cosmologists confront a tension between theory and observation. The supervoid is too large, too empty, too aligned with the cold spot to be ignored. If it arises from a breakdown or subtle alteration of gravity at cosmological scales, it could point to a universe where the laws of physics evolve with scale, where underdense regions behave differently from overdense ones, and where the largest anomalies hide secrets that ordinary theory cannot predict. Every measurement, from galaxy surveys to weak lensing maps to the cosmic microwave background, tests how gravity shapes the universe. The Eridanus Supervoid stands as a stark reminder that while our models work almost everywhere, there are corners of the cosmos where the rules are pushed to the extreme. Modified gravity remains a tantalizing possibility, a glimpse at a reality where gravity itself might be more flexible than we imagine, capable of producing the vast emptiness that has puzzled astronomers and shaped one of the most enigmatic features in the observable universe. Statistical fluke argument. The Eridanus Supervoid and its alignment with the cold spot have sparked intense debate. One of the earliest responses from skeptics was to call it a statistical fluke, an improbable but ultimately random feature in the cosmic microwave background. The universe is vast, and with millions of points in the sky, it seems almost inevitable that a few unusual patterns will appear purely by chance. This line of reasoning is called the look elsewhere effect, the idea that when you examine enough regions, one of them will stand out no matter what. A coal patch, they argued, could simply be the universe playing dice, a natural fluctuation in the sea of randomness. At first glance, this seemed plausible. Cosmic microwave background maps are full of small temperature variations. Some are just noise, others are the result of normal density fluctuations. Could the cold spot be nothing more than one of these outliers, a rare but harmless coincidence? Early studies leaned on this argument, suggesting that the probability of seeing a spot this extreme is low but not impossible if the entire sky is considered. It was a statistical shrug, a way to explain away the anomaly without revising cosmology or invoking exotic physics. However, the look elsewhere argument begins to crumble when new data comes into play. As more detailed maps appeared, from WMAP to Planck, the cold spot persisted. It wasn't washed out by higher resolution or more precise measurements. It remained coherent, localized, and extreme. The same region also aligned with the Eridanus Supervoid, revealed through multiple galaxy surveys across different wavelengths. This combination makes the coincidence argument increasingly difficult to sustain. A single anomaly could be dismissed as a fluke, but a coincident alignment between two independent datasets stretches the limits of probability. Repeated detections strengthen the challenge to the fluke explanation. The cold spot is confirmed in the temperature maps of WMAP and Planck, two instruments with entirely different systems, calibration and observation methods. The Eridanus Supervoid is observed in optical surveys like SDSS and DES, as well as in infrared maps like Tubular ISE-2MASS. Multiple independent lines of evidence all point to the same patch of sky, indicating that it is a real, physical structure, not a statistical ghost. Each new confirmation chips away at the idea that the feature could arise from chance alone. The statistical fluke argument also fails when considering the scale of the anomaly. Most random fluctuations in a Gaussian universe are small and local. The cold spot, coupled with a void hundreds of millions of light years across, is not a small blip. It is a coherent, structured feature that spans enormous distances. Random chance can create small deviations, but producing something of this magnitude, precisely aligned in both the cosmic microwave background and the galaxy distribution, defies what statistics would normally allow. The odds are no longer just low, they are astronomically low. The fluke argument struggles when confronted with three-dimensional reconstruction. The void is not a projection effect or a mere coincidence in angular space. Redshift data shows that matter is genuinely missing along the line of sight, confirming that the anomaly has depth as well as width. The statistical fluke argument cannot account for both the temperature decrement in the CMB and the physical absence of galaxies in the same region. It fails to bridge the gap between a two-dimensional map and the real three-dimensional universe. Even attempts to modify probability estimates to accommodate the look elsewhere effect run into trouble. Analysts can argue that scanning the entire sky should produce outliers, but the number of extreme events predicted by Gaussian statistics is far smaller than the combination of the cold spot and the supervoid. Every additional survey, every new wavelength, every more precise measurement tightens the statistical noose. Instead of making the feature more likely as a coincidence, new data makes it less likely. What was once an uncomfortable outlier becomes a glaring, inescapable anomaly. The repeated detection across independent instruments and surveys also eliminates concerns about observational bias. If a fluke were caused by instrument noise, calibration errors, or foreground contamination, it would not appear consistently in multiple datasets with different sensitivities, filters, and methodologies. The fact that the cold spot and the supervoid appear in both microwave and optical/infrared data simultaneously shows that this is not an artifact of the measurement process. It is a feature of the universe itself. Even simulations designed to test the likelihood of random flukes reinforce the point. Large-scale cosmological simulations that generate millions of mock universes rarely, if ever, produce a feature with the combination of size, depth, and alignment observed in the cold spot and the Eridanus Supervoid. Statistically, it sits far outside the expected distribution of anomalies. This is not a single 1 in 1,000 event. It is a 1 in several million or more event when all factors are considered. In short, the statistical fluke argument cannot survive the accumulation of evidence. The cold spot is too coherent, the void is too large, and the alignment between them is too precise. Repeated detections across multiple instruments and wavelengths demonstrate that this is not a random occurrence in the cosmic microwave background, but a physical structure in the universe. Each new confirmation erodes the credibility of coincidence as an explanation, forcing the scientific community to acknowledge that the universe has produced a feature that sits on the extreme edge of possibility. The look elsewhere effect may explain minor anomalies, small bumps in the cosmic microwave background, but it cannot account for a feature that is simultaneously vast, coherent, and confirmed by independent surveys. The statistical fluke argument is overwhelmed by the scale and depth of the Eridanus Supervoid and the cold spot. Each layer of observation, microwave, optical, infrared, redshift, adds certainty, transforming what might have been dismissed as a fluke into a striking, undeniable cosmic oddity. As the data pile up, statistical arguments lose force, the cold spot refuses to disappear, and the void refuses to fill in. Random chance becomes increasingly implausible. The universe presents not just an oddity, but a coherent structure that challenges the limits of probability, showing that what once seemed like a possible fluke is, in fact, one of the most extraordinary and puzzling features ever observed in the cosmos. The cold spot and the Eridanus Supervoid sparked excitement, but excitement always comes with suspicion. Could this feature be an illusion? Could dust, radio sources, or galactic contamination be masquerading as something extraordinary? Foreground and systematics checks. Cosmic microwave background maps are sensitive instruments capturing tiny temperature variations in the oldest light in the universe. Even small foregrounds can distort the picture, creating false cold or hot spots if not accounted for. Galactic dust is one of the biggest culprits. Our own Milky Way emits infrared and microwave radiation that can overlay the cosmic signal. A dense patch of dust along the line of sight can appear colder or warmer, depending on frequency, producing the illusion of a cosmic anomaly. Radio sources, bright active galaxies, and other foreground emitters also have the potential to contaminate maps. Each source can inject noise, skewing the measured temperature and creating features that might look like real structures in the early universe. Scientists took these concerns seriously. They applied rigorous foreground subtraction methods, separating the galactic signal from the primordial background. Different frequency bands were compared because galactic dust and radio sources affect each frequency differently. If the cold spot were caused by contamination, its signature would vary across frequencies. Observations, however, showed remarkable consistency. The cold region appeared in multiple frequency bands with the same shape, location, and amplitude. Foreground effects could not mimic the anomaly across the board. Instrument bias was another concern. Measuring microkelvin variations in the cosmic microwave background pushes technology to the limit. Detectors have their quirks. Electronics can introduce artifacts, and scanning patterns can imprint false features. Yet the cold spot appeared in both WMAP and Planck data, two satellites with entirely different instruments, designs, and observation strategies. Each mission had its own systematics, its own calibration methods, and its own error patterns. The fact that both observed the cold spot in the same position with the same properties rules out simple instrument error as the explanation. Cross-checks extended beyond satellites. Ground-based telescopes and balloon experiments also scanned the relevant region of the sky. The feature persisted, demonstrating that no single instrument or method created the anomaly. Multiple independent measurements confirmed it. The consistency across instruments, frequencies, and observational platforms strengthened the case that the cold spot was a real feature, not a mirage caused by foregrounds or systematic errors. Foreground contamination would leave telltale signs. Dust maps, radio surveys, and catalogues of galactic sources were examined, and no correlation appeared between the cold region and known contaminants. If the cold spot was simply a dust lane or an active radio source, astronomers would have found a matching pattern. Nothing of the sort exists. The area of the sky is remarkably clean, with low galactic emission, and the underdensity traced by galaxy surveys aligns perfectly with the location of the cold spot. Galactic contamination can warp small-scale features, but the cold spot spans tens of degrees in the sky. Creating a false feature of that size and amplitude from local foregrounds would require an extreme, unprecedented anomaly in our own galaxy's emission. No evidence supports such an extreme. The simplest explanation from contamination is already more complicated than treating the feature as real, giving weight to the idea that the universe itself produced it. Every frequency, every instrument, every independent observation paints the same picture. The same patch of sky stands out as colder than expected. The same region shows a deficit of galaxies, consistent with an underdensity along the line of sight. The cold spot is not an artifact of microwave detectors, not a glitch in scanning electronics, and not a shadow from galactic dust or radio emission. Even subtle systematics were tested. Beam shapes, scanning strategies, and time-dependent variations in instrument sensitivity were modelled and compared with the observed feature. None of these tests could account for the cold spot's size, shape, or alignment. Models of foreground subtraction, when applied independently, left the anomaly intact. Independent instruments, independent teams, independent techniques all converged on the same result. Dust, radio sources, galactic emission, and instrumental bias might create small blips in maps, but the cold spot and the supervoid persist across all these checks. Each layer of analysis confirms the reality of the feature. The universe is speaking through multiple channels. The photons are arriving cold, the galaxies are absent, and the instruments agree. Foregrounds and systematics can no longer be used to explain away what is clearly a profound and mysterious cosmic structure. Even after decades of scrutiny, the anomaly remains unshaken. Every new map, every refined instrument, and every independent survey adds clarity. The cold spot survives rigorous testing, appearing consistently across instruments designed decades apart, at different frequencies, and with independent observation methods. Dust maps show no interference. Radio catalogues show no alignment. Galactic contamination cannot reproduce the vast coherence observed in both the CMB and galaxy surveys. The Eridanus Supervoid and the cold spot form a cosmic duet. Photons leave the early universe carrying the imprint of an underdensity. Surveys of galaxies trace the same emptiness in 3 dimensions. Multiple instruments confirm the same signal, immune to dust, radio sources, or any local contaminant. Systematics checks fail to find an alternative explanation. Every verification adds weight, transforming skepticism into recognition that the universe itself is responsible for this extraordinary feature. The cold spot's survival across instruments and frequencies is remarkable. WMAP detected it first, Planck confirmed it with higher resolution, and optical and infrared surveys revealed the underdensity in galaxies. Each dataset adds a layer of confirmation. Each test of foregrounds, dust, or radio sources eliminates more alternative explanations. The feature is too coherent, too large, and too persistent to be anything other than real. Instrument bias would require multiple satellites and telescopes operating decades apart with entirely independent designs to all create the same false signal in the same location. No known systematic could mimic the cold spot on such a scale. Every photon, every galaxy, every map tells the same story. An extraordinary region exists in the universe, cold in the cosmic microwave background and empty of matter along our line of sight. Even subtle signals, like weak lensing distortions, reinforce the story. The lack of matter in the Eridanus Supervoid affects the gravitational lensing of background galaxies, and the effect is consistent with the CMB cold patch. Foregrounds cannot replicate this alignment between temperature decrement, galaxy density, and gravitational lensing. Systematics are simply incapable of creating such a multifaceted, multi-wavelength coincidence. Every check, every cross-comparison, every instrument and survey converges on one undeniable fact: the cold spot and the Eridanus Supervoid are real. Dust, radio sources, and galactic contamination fail to explain them. Instrument biases cannot account for them. Independent instruments, independent teams, independent methods all see the same phenomenon. The universe produced a structure that is large, coherent, and undeniable, and it resists all attempts to dismiss it as a foreground or systematic error. Alternative void reconstructions. Mapping the universe is never straightforward. Galaxies are not evenly spaced, and surveys can only sample a fraction of the cosmos at any given time. To define a void, astronomers rely on algorithms, mathematical tools that identify regions where matter is missing. Each algorithm has its own assumptions, its own method for deciding what counts as empty, and its own sensitivity to noise and survey limitations. Some algorithms are conservative, labeling only the clearest underdensities as voids. Others are aggressive, stretching definitions to include marginally underdense regions that might otherwise be dismissed. Conservative algorithms aim to avoid overestimating emptiness. They require a significant drop in galaxy density compared to the cosmic average before calling a region a void. These methods focus on high-confidence underdensities, demanding that multiple redshift slices show a consistent deficit of galaxies. Even with these strict thresholds, the Eridanus Supervoid appears. It is large enough, deep enough, and coherent enough that no conservative criteria can erase it from the map. The universe presents a void so extreme that even cautious definitions cannot deny its existence. Aggressive algorithms, on the other hand, expand void boundaries, linking smaller underdense regions into larger structures. They tend to exaggerate void sizes, sometimes merging separate features into one continuous underdensity. Applying these methods to the same region amplifies the anomaly, creating a supervoid that stretches further and dips even deeper than initial estimates. While conservative algorithms already reveal the void, aggressive approaches make it undeniable, highlighting its full extent and revealing subtleties that conservative methods might miss. Different void-finding algorithms also test the sensitivity of results to survey geometry and galaxy sampling. Some algorithms work in 3 dimensions, using redshift to reconstruct distance and shape. Others project galaxy positions into angular maps, estimating emptiness along a line of sight. Cross-checking these methods ensures that the Eridanus Supervoid is not an artifact of how galaxies were counted or mapped. The feature persists across all techniques, with slight variations in shape or depth, but consistent presence. No algorithm reduces it to a statistical quirk or eliminates it entirely. Threshold selection plays a critical role. A more lenient threshold allows regions with moderate underdensity to be included, potentially merging smaller voids into a vast, continuous structure. A stricter threshold identifies only the deepest underdensities, giving a minimal representation of the void. In the case of the Eridanus Supervoid, even the strictest thresholds leave a massive anomaly. The void remains hundreds of millions of light-years across, with a density contrast far below the cosmic average. It is not an artifact of how thresholds are set. The anomaly is robust against reasonable variations in criteria. Alternative reconstructions also reveal details about geometry and layering. While some methods assume voids are roughly spherical, 3-dimensional reconstructions show elongation along the line of sight. The supervoid may consist of overlapping underdensities, creating a layered structure that enhances its apparent size. Conservative algorithms detect the core of the underdensity, while aggressive algorithms capture the surrounding lower density shells, producing a more complete picture of the void's complexity. Both approaches confirm that the anomaly is real, not a product of modeling choices. Void-finding algorithms are designed to test the limits of detection. By varying parameters such as minimum galaxy count, smoothing scales, and connectivity criteria, astronomers can explore how sensitive their results are to survey uncertainties. Even under the most cautious reconstructions, the Eridanus Supervoid persists. Its depth, size, and coherence are too extreme to be an artifact of algorithm choice. Every method, from simple density thresholding to sophisticated watershed and tessellation techniques, identifies a substantial underdensity in the same location. The alignment with the cold spot further strengthens the case. Multiple void-finding techniques using independent surveys place the supervoid along the same line of sight as the anomalous region in the cosmic microwave background. Conservative algorithms map the deepest core, aggressive algorithms capture extended layers, yet all reconstructions point to the same conclusion. The region is genuinely underdense, and the scale of emptiness is extraordinary. Even when accounting for survey limitations, such as gaps in coverage, incomplete redshift measurements, and observational noise, the void remains prominent. Algorithms can correct for these factors, weighting galaxies according to completeness or applying statistical methods to fill missing data. Regardless of these adjustments, the anomaly does not vanish. The supervoid is large enough, deep enough, and coherent enough to survive any reasonable correction, demonstrating that it is a real feature of the universe, not a quirk of observation. Alternative reconstructions also test whether projection effects could exaggerate the void. Some algorithms analyze voids along the line of sight, checking whether the apparent emptiness arises from a chance alignment of smaller, unrelated underdensities. Three-dimensional methods using redshift data confirm that the supervoid is extended along the line of sight, with a genuine deficit of galaxies across hundreds of millions of light-years. Projection cannot explain the anomaly. It exists in space, not just in the map. The persistence of the Eridanus Supervoid across different void-finding algorithms demonstrates its robustness. Conservative thresholds capture the core underdensity. Aggressive thresholds reveal extended layers, and variations in methodology confirm that the anomaly is independent of technique. Every reconstruction, regardless of assumptions, finds a massive, coherent underdensity at the same location. The void cannot be dismissed as a minor fluctuation, an artifact of threshold choice, or a quirk of mapping methods. Different reconstructions also provide insight into the void's physical properties. Core density, surrounding shell contrast, elongation, and substructure can all be measured with alternative algorithms, offering a more complete picture of the supervoid. The anomaly is not a uniform emptiness, but a structured, layered region with distinct density variations, further distinguishing it from normal voids. The complexity revealed by multiple reconstructions highlights how extreme and unusual this feature truly is, confirming that it defies standard expectations for cosmic voids. Even in the most minimal definitions, the Eridanus Supervoid dominates its region of the sky. Conservative methods identify a deep core with significantly reduced galaxy density, while aggressive methods reveal a broader, layered structure extending hundreds of millions of light-years. No algorithm eliminates the anomaly. No threshold reduces it to insignificance. Across all alternative reconstructions, the void remains one of the largest, deepest, and most coherent structures ever observed, defying expectations and challenging current models of cosmic structure formation. What new telescopes say? Planck's finding. When WMAP first revealed the cold spot, it shocked the cosmology community. The maps showed a region colder than expected, hinting at something unusual in the early universe. WMAP's resolution was good for its time, but fine details remained unclear. The size, depth, and exact shape of the cold spot could only be estimated, and doubts lingered about whether it was a genuine anomaly or a quirk of instrument sensitivity and data processing. Scientists needed a telescope with higher resolution, greater sensitivity, and broader frequency coverage to confirm the feature and refine measurements. That telescope was Planck. Planck was designed to surpass WMAP in almost every metric. Its detectors captured the cosmic microwave background across 9 frequency bands, from low-frequency microwaves to high-frequency infrared signals. The improved resolution allowed astronomers to examine temperature variations on smaller scales, distinguishing true cosmic features from noise or foreground contamination. Planck also mapped the entire sky with unprecedented uniformity, eliminating gaps or artifacts that could create false patterns in the WMAP data. The combination of higher resolution, multiple frequencies, and full sky coverage made Planck the ultimate tool to validate or refute anomalies like the cold spot. When Planck released its first maps, the cold spot was immediately visible in the same location as WMAP's maps, with slightly more precise coordinates. Its amplitude was consistent with previous measurements, confirming that it was a real temperature decrement in the cosmic microwave background, not an artifact of data processing. Planck revealed subtle details about the shape of the region, showing that it was larger and slightly more elongated than WMAP suggested, stretching over tens of degrees in the sky. These measurements refined the statistical significance of the anomaly, making it clear that the cold spot was more than a minor fluctuation. Planck also allowed for better separation of foreground contamination. With 9 frequency bands, it was possible to isolate galactic dust, synchrotron radiation, and extragalactic radio sources, minimizing their contribution to the observed signal. The cold spot persisted through rigorous foreground subtraction, demonstrating that it was not caused by dust lanes in the Milky Way or bright radio galaxies along the line of sight. The anomaly remained significant even when multiple independent foreground models were applied, confirming that the cold region represents a true deviation in the cosmic microwave background. Improved resolution also helped test competing hypotheses. Smaller scale features inside the cold spot became visible, revealing slight temperature variations that suggested some internal structure. The data could be compared with models of voids, inflationary fluctuations, and exotic scenarios like bubble collisions. Planck reduced uncertainties in the amplitude, size, and shape of the cold spot. But none of these refinements eliminated the anomaly. Its presence remained robust across all frequency bands and analysis methods, making it clear that the feature is a genuine cosmological signal. Planck's observations also allowed for cross-checks with other datasets. Regions corresponding to the cold spot were compared to galaxy surveys, weak lensing maps, and infrared measurements. The alignment with an underdense region in galaxy distribution strengthened the connection between the cold spot and the Eridanus Supervoid. The telescope's high-resolution data enabled detailed studies of potential links between cosmic structures and temperature variations in the microwave background, providing new ways to quantify the relationship. One of Planck's key contributions was reducing uncertainty in statistical analysis. Pure map data left some ambiguity about whether the cold spot could arise from Gaussian fluctuations in a standard cosmological model. Planck's high-resolution measurements narrowed the confidence intervals, showing that the probability of observing such a large, cold region by chance is extremely low. This placed stronger constraints on theoretical models, forcing a closer look at extreme voids, anomalies in inflation, or potential physics beyond standard cosmology. The telescope's final word did not resolve the mystery, but sharpened it. The cold spot is no longer a blurry feature in low-resolution maps. Its amplitude, size, and coherence are well characterized, with uncertainties reduced to levels that leave little room for statistical or instrumental excuses. The anomaly persists, compelling cosmologists to confront the fact that the universe has produced a structure that sits at the extreme edge of what standard models predict. Planck also revealed subtle correlations with other features in the cosmic microwave background. Slight temperature gradients, alignments with other large-scale anomalies, and potential low multipole patterns were explored to see if the cold spot was part of a larger cosmic signal. Although interpretations remain debated, Planck data provided the first chance to test these ideas with high precision, giving scientists tools to connect the cold spot to broader questions about cosmic structure and the early universe. The high fidelity of Planck's maps confirmed the cold spot across multiple independent analyses. Teams using different processing pipelines, foreground models, and statistical methods all recovered the same feature. The anomaly's presence is no longer in question. Its reality is reinforced not by a single instrument, but by multiple independent observations converging on the same unusual region of the sky. Planck's final maps also offer insight into the temperature profile across the cold spot. The central region is noticeably colder than its surroundings, and a gradient extends outward, tapering off over several degrees. These measurements enable simulations of potential void effects, predictions for integrated Sachs-Wolf contributions, and tests of alternative explanations like non-Gaussian fluctuations or exotic early universe physics. The telescope transformed what was once a mysterious cold patch into a detailed dataset, suitable for rigorous cosmological analysis. Although Planck reduced uncertainties and refined measurements, the anomaly persists. It remains a coherent, significant feature that cannot be dismissed as noise, foreground, or instrumental error. The improved resolution, better frequency coverage, and higher sensitivity strengthen confidence in its reality. The cold spot survives as one of the most remarkable and puzzling features of the cosmic microwave background, confirmed at a level of detail and precision that WMAP could not provide, cementing its status as a true anomaly demanding explanation. The Vera Rubin Observatory's role. The Vera Rubin Observatory, built to host the legacy survey of space and time, is changing how astronomers see the universe. Unlike previous surveys that map portions of the sky or limited galaxy populations, the Rubin Observatory will chart billions of galaxies across most of the southern sky. This massive dataset allows astronomers to probe cosmic structures with unprecedented detail. Regions once considered sparse or uncertain will be measured with precision, revealing not just the edges of voids, but their interiors, gradients, and subtle features. The Legacy Survey of Space and Time, or LSST, will repeatedly image the same regions over 10 years. With each pass, fainter galaxies are detected, redshift estimates improve, and photometric accuracy increases. This approach creates a three-dimensional picture of the universe that is far richer than any previous survey. Where WISE, 2-mass, SDSS, or DES could only trace a fraction of galaxies, LSST captures an enormous volume of cosmic history, allowing voids like the Eridanus Supervoid to be mapped in detail rather than inferred from limited samples. Voids are defined not just by the absence of bright galaxies, but also by subtle reductions in faint galaxy populations. LSST's depth will identify these faint galaxies, clarifying whether the underdensity in a given region is a true lack of matter or simply a sampling artifact. By mapping both bright and faint galaxies, LSST will probe the interiors of supervoids with unprecedented resolution, revealing how density changes from the center outward and whether structures inside the void, such as smaller clumps or filaments, exist. The ability to reconstruct the full three-dimensional shape of voids depends on accurate distance measurements. LSST will provide photometric redshifts for billions of galaxies, allowing astronomers to slice the universe along the line of sight. This slicing turns a projected underdensity on the sky into a volumetric map of matter distribution. For the Eridanus Supervoid, LSST will determine whether the void is elongated, layered, or fragmented, offering a clear picture of its true geometry and depth. Density debates surrounding the cold spot and the supervoid hinge on precise measurements. Previous surveys struggled with sample variance. When only part of a void is observed, its true density contrast remains uncertain. LSST's wide coverage mitigates this problem, capturing the full volume of underdense regions and providing robust statistics. This allows the calculation of average density, density fluctuations, and the contrast between the void and the cosmic mean with unprecedented confidence. The interior of the void, once speculative, becomes measurable. LSST's repeated observations also provide cross-checks for systematic errors. Photometric calibration, star-galaxy separation, and atmospheric effects can all affect galaxy counts. By imaging the same area hundreds of times under varying conditions, the Rubin Observatory can correct for these effects, ensuring that underdensities are not artifacts of observation. This reliability makes the resulting void maps highly trustworthy and capable of settling debates about the Eridanus Supervoid's true density and structure. One of the most exciting aspects of LSST is the ability to identify subtle gradients within voids. Voids are not perfectly empty. They contain low-density filaments and small galaxy groups. LSST's depth will capture these structures, revealing the internal dynamics of the void and how matter is distributed. This information is critical for testing theoretical models of void formation and for evaluating whether the observed underdensity is consistent with standard cosmology or hints at something more exotic. Beyond counting galaxies, LSST enables weak lensing studies inside voids. Light from background galaxies bends slightly as it passes through underdense regions. Measuring these distortions provides an independent check on mass distribution, confirming whether the apparent emptiness is matched by a true deficit of matter. The combination of galaxy counts and lensing maps creates a multi-dimensional view of voids, offering direct tests of the theories used to explain the cold spot and the Eridanus Supervoid. LSST's scope also allows rare voids to be studied statistically. Previous surveys could identify individual anomalies, but their significance was difficult to quantify because similar features were scarce. LSST's billions of galaxies make it possible to search for large voids across a vast volume, establishing whether structures like the Eridanus Supervoid are unique or part of a broader population of extreme underdensities. Understanding this distribution informs the limits of standard cosmology and test predictions from simulations. The observatory's long-term operation adds temporal depth as well. LSST will detect transient phenomena and monitor variability across cosmic structures. While voids themselves evolve slowly, the ability to track small changes and cross-correlate with galaxy populations over time helps refine models of structure growth. For supervoids, this means seeing not just static emptiness, but the dynamic context in which these anomalies exist. LSST's combination of depth, coverage, and precision marks a turning point in void studies. The observatory can finally answer questions about size, density, and internal structure that were previously speculative. The alignment with the cold spot can be tested more rigorously, comparing CMB anomalies with precise three-dimensional maps of galaxies. If the Eridanus Supervoid truly corresponds to the cold spot, LSST will provide the clearest evidence yet. By mapping faint galaxies, revealing subtle structures inside voids, and measuring true matter distributions with lensing, LSST moves the study of the universe from inference to direct measurement. The Eridanus Supervoid, once a partially understood anomaly, becomes a tangible region of space to analyze, quantify, and compare with theory. Rubin Observatory's data will allow scientists to test whether the supervoid is extreme but allowable within standard cosmology, or whether it hints at new physics, pushing models of structure formation to their limits. The legacy survey of space and time opens a new chapter in cosmic mapping. Regions that once appeared as vague patches of emptiness will be charted in fine detail. For anomalies like the Eridanus Supervoid, the observatory provides both the depth and the scale needed to settle density debates, clarify structure, and connect the underdensity to cosmic microwave background anomalies. LSST transforms speculation into data, enabling a complete picture of void interiors that was previously impossible. Euclid and Roman Space Telescope. The next generation of space telescopes promises to transform the way cosmic structures are understood. Euclid and the Nancy Grace Roman Space Telescope are designed to map the distribution of matter across vast stretches of the universe with precision that ground-based surveys cannot match. Unlike surveys that rely on counting galaxies alone, these telescopes use weak gravitational lensing to measure the total mass of structures, including dark matter, in 3 dimensions. This approach allows a direct comparison between the visible galaxy distribution and the underlying gravitational field. Weak lensing is subtle. Light from distant galaxies bends slightly as it passes through regions of varying mass. Over billions of galaxies, these tiny distortions accumulate into a measurable signal, revealing where matter is concentrated and where it is missing. Euclid will scan billions of galaxies across a large fraction of the sky, mapping weak lensing signals with high resolution and uniformity. The Nancy Grace Roman Space Telescope will complement this with its wide-field imaging, reaching fainter galaxies and adding depth to the mass map. Together, these missions will provide an unprecedented view of the cosmic web. For the Eridanus Supervoid, weak lensing offers the most direct test of its existence and scale. Galaxy surveys have traced an underdensity, but absence of galaxies does not always equate to absence of matter. Dark matter could still fill the void, unseen by optical and infrared observations. Weak lensing maps allow scientists to measure the true gravitational deficit in the region, confirming whether the cold spot's corresponding supervoid is an actual absence of mass rather than a statistical or observational artifact. Euclid's Wide Area Survey covers the southern sky, overlapping with regions mapped by the Rubin Observatory. By combining galaxy counts with lensing maps, the mission can reconstruct three-dimensional density profiles across the supervoid. It will reveal whether the interior is smooth or layered, whether the central underdensity is as deep as current estimates suggest, and whether smaller structures punctuate the emptiness. These details are critical for evaluating theoretical models of supervoid formation and understanding how such a structure interacts with the cosmic microwave background. The Nancy Grace Roman Space Telescope adds complementary capabilities. Its high-resolution imaging allows weak lensing measurements for fainter, more distant galaxies, probing larger volumes of space along the line of sight to the cold spot. Roman's depth is essential for detecting subtle distortions from low-density regions, where galaxy counts alone might underestimate mass deficits. By extending the lensing map farther into the universe, Roman will help determine the full extent and shape of the Eridanus Supervoid. Confirmation of the supervoid through weak lensing would be transformative. A direct measurement showing a substantial deficit of matter aligned with the cold spot would link the cosmic microwave background anomaly to a tangible structure. The temperature decrement observed in the CMB could then be connected to the integrated Sachs-Wolf effect, where photons lose energy passing through an underdense region. Measuring the mass directly allows models to predict the expected temperature drop more accurately, testing whether standard cosmology can accommodate such extreme features. Refutation is equally informative. If weak lensing shows that matter is largely present within the region of the cold spot, then the apparent galaxy underdensity would need a different explanation. Perhaps it is a statistical artifact of previous surveys, or a projection effect where smaller underdensities line up along the line of sight to mimic a single supervoid. Such a result would constrain theories of void formation and force a re-evaluation of assumptions about the link between galaxy counts and mass distribution. Both Euclid and Roman are designed to operate over long periods with repeated observations, reducing systematic errors. Variations in telescope sensitivity, calibration uncertainties, and instrumental effects can all bias weak lensing measurements, but repeated imaging, multi-filter coverage, and overlapping fields allow cross-checks and corrections. The result will be mass maps with precision high enough to detect deficits of a few percent across hundreds of millions of light years, sufficient to test the Eridanus Supervoid hypothesis directly. The telescopes also enable statistical studies of extreme voids. By surveying billions of galaxies across the sky, Euclid and Roman will identify rare underdensities comparable in scale to Eridanus. Comparing the frequency and properties of these voids with simulations tests whether the observed supervoid is a plausible feature within standard cosmology or an outlier that challenges existing models. Weak lensing adds an independent layer showing whether similar underdensities in galaxy counts correspond to true deficits of mass. Combining the capabilities of Euclid, Roman, and Rubin Observatory creates a powerful trifecta for cosmic mapping. Rubin provides deep, multi-epoch galaxy counts, revealing the structure of void interiors. Euclid measures mass over large scales using weak lensing, verifying density contrasts across the cosmic web. Roman reaches fainter galaxies and adds depth, confirming underdensities along extended lines of sight. Together, they can resolve ambiguities about the Eridanus Supervoid, including its true size, shape, density, and connection to the cold spot. Weak lensing measurements will also clarify the internal structure of the void. Subtle filaments and clumps that exist within the region can be detected, showing whether the underdensity is uniform or contains residual matter. These details inform theoretical models of void evolution, gravitational influence, and photon energy loss in the early universe. Accurate mass maps allow predictions of the expected temperature decrement in the CMB and test whether known physics can reproduce the observed cold spot. The synergy of galaxy counts and lensing also allows the separation of baryonic and dark matter contributions. Faint galaxies provide one estimate of visible matter, while lensing measures total gravitational influence, dominated by dark matter. By comparing the two, Euclid and Roman can determine whether the supervoid is a true void in total mass or primarily a deficit of luminous matter. This distinction is critical for understanding whether the cold spot corresponds to a deep gravitational underdensity or a more subtle variation in visible galaxies. Both telescopes will repeatedly scan overlapping regions, allowing cross-calibration and consistency checks. Systematic errors, observational biases, or uncorrected instrumental effects are minimized through redundancy. The robustness of these measurements ensures that mass mapping is reliable, capable of confirming or refuting the presence of a supervoid with unprecedented confidence. Observations from Euclid and Roman will also feed directly into cosmological simulations. By providing precise three-dimensional mass distributions, these datasets allow theorists to test the limits of structure formation models, inflation predictions, and dark energy influences. If the supervoid is confirmed, simulations will be challenged to reproduce it. If not, constraints on extreme void formation and alignment with the cold spot will refine theories of cosmic evolution. A crack in the standard model of cosmology. The discovery of a massive, mysterious underdensity in the universe strikes at the heart of cosmology. The lambda CDM model, lambda cold dark matter, has been the standard framework for understanding the cosmos. It explains the cosmic microwave background, the distribution of galaxies, the accelerating expansion, and the growth of structure over billions of years. Predictions from lambda CDM have matched observations across multiple scales, giving scientists confidence that they understand the large-scale structure of the universe. The model is elegant, tested, and widely used to simulate the evolution of the cosmos from the earliest moments after the Big Bang to the present day. Despite its successes, science advances when anomalies appear. Unexplained features in the data force scientists to ask hard questions. Is there a flaw in measurement, a missing piece in theory, or evidence for new physics? The Eridanus Supervoid, aligned with the cold spot, is precisely this kind of anomaly. It challenges the limits of lambda CDM, testing assumptions about cosmic uniformity and the statistical bounds of void formation. Historical surprises in cosmology have led to major advances. The discovery of cosmic acceleration, dark energy, and even the existence of dark matter itself all began as unexplained anomalies that forced a re-evaluation of accepted theory. The universe has a track record of revealing its secrets through deviations from expectation, and the cold spot might be the next chapter in that story. If the supervoid is real and unique, the implications are profound. The standard model assumes the universe is statistically homogeneous at large scales, meaning that over hundreds of millions of light years, matter should average out to predictable densities. A single, extremely underdense region tests that assumption. It constrains theories of inflation, the rapid expansion that set initial density fluctuations in the early universe. Inflation predicts Gaussian fluctuations and a smooth, uniform distribution of matter at the larger scales. A void of this magnitude may suggest that the early universe experienced an unusual fluctuation, one outside the expected statistical bounds. It forces theorists to reconsider whether inflation is fully understood, whether rare anomalies can occur, and what mechanisms might produce them. Limits on cosmic uniformity are equally important. If such a hole is unique, it may represent a rare statistical outlier. Cosmologists can accommodate it as an extreme event, acknowledging its improbability while keeping the broader model intact. However, even a single supervoid provides a laboratory for testing the most fundamental assumptions of cosmology, that the universe looks roughly the same in every direction, and that density variations at large scales follow predictable patterns. The existence of one massive anomaly stretches those assumptions, demanding new simulations, deeper surveys, and refined theoretical models. If there are more holes, the challenge becomes far more severe. The presence of one anomaly might be survivable within lambda CDM, treated as an extreme but possible fluctuation. Multiple anomalies would undermine the statistical framework that underpins the model. It would suggest that the universe is far less uniform than previously believed, that large-scale structure can produce voids of unexpected size and depth, and that current simulations have underestimated the extremes of cosmic evolution. Early hints of similar features in other regions of the sky raise the possibility that the Eridanus Supervoid is not alone. These observations, though preliminary, hint at a pattern that could challenge the core of cosmological theory, forcing scientists to revisit assumptions about density fluctuations, void formation, and the physics of the early universe. The stakes extend beyond a single cosmic anomaly. Each supervoid, if real, provides direct constraints on the initial conditions set by inflation, the growth of structure over billions of years, and the role of dark energy in shaping large-scale cosmic expansion. Detecting multiple supervoids would redefine expectations for the universe's statistical homogeneity, pushing cosmology into new territory, where rare events are no longer outliers, but features requiring explanation. Observing and mapping these regions with instruments like LSST, Euclid, and Roman will determine whether the universe contains isolated curiosities or hints at a hidden pattern in its large-scale structure. Understanding the implications requires considering the connection to the cosmic microwave background. The cold spot is already unusual, and if it corresponds to a massive void, the phenomenon ties early universe physics to late-time structure formation in a way that is rarely tested. One anomaly tests inflation models and cosmic uniformity. Multiple anomalies would create a chain reaction of questions about structure growth, dark energy, and the statistical assumptions built into lambda CDM. The universe could be signaling that the standard model, while successful in many respects, is incomplete when confronted with extremes of scale and mass distribution. The scientific process thrives on anomalies. Observations like the Eridanus Supervoid drive the development of new theoretical frameworks, inspire the design of next-generation telescopes, and motivate more precise mapping of cosmic structure. They encourage cross-checks between galaxy surveys, weak lensing measurements, and microwave background data. The outcome, whether confirming the uniqueness of the whole or revealing a population of similar voids, will have lasting consequences for how cosmologists understand the universe. Large anomalies also influence simulations. If the Eridanus Supervoid exists as measured, numerical models of structure formation must account for how such extreme voids can emerge from standard initial conditions. Simulations that cannot reproduce the observed void challenge the sufficiency of current physics, whether related to inflation, dark energy, or dark matter clustering. Multiple voids would exponentially increase this challenge, making the universe itself a testing ground for theories pushed to their limits. Observational programs are poised to test these questions directly. LSST, Euclid, and Roman will map galaxies, measure weak lensing, and quantify the matter distribution in and around these voids. The combination of galaxy counts, three-dimensional structure, and lensing-derived mass maps will provide the strongest evidence yet for whether these supervoids exist as true gravitational deficits. This comprehensive approach offers the chance to move from speculative anomaly to measurable feature, connecting observations across multiple wavelengths, techniques, and instruments. If one anomaly exists, it informs the boundaries of standard cosmology. If multiple anomalies appear, it may rewrite them. The presence or absence of similar structures elsewhere in the universe will influence how scientists interpret the statistical limits of lambda CDM and the underlying physics of the early universe. Each potential supervoid becomes a probe of cosmic history, linking the physics of the first fractions of a second after the Big Bang to the distribution of matter billions of years later. The cold spot and its associated supervoid represent more than a single oddity. They are a window into extremes of structure formation, a test of inflationary theory, a measure of cosmic uniformity, and a challenge to existing simulations. The presence of even one supervoid stretches the standard model. The discovery of more could force a fundamental rethinking of how the universe evolves, how rare events manifest, and how large-scale structure shapes the observable cosmos. The universe is not a finished picture. Every new survey, telescope, and mission adds detail, filling gaps in the cosmic map and revealing structures that were invisible before. What once looked uniform and predictable now shows patches of complexity, regions of unexpected emptiness, and anomalies that challenge assumptions about scale and matter distribution. The Eridanus Supervoid sits at the center of this unfolding story, a stark reminder that our understanding of the cosmos is still incomplete. This hole is one of the most serious large-scale anomalies ever observed. Its sheer size, depth, and alignment with the cold spot make it unlike typical voids in the cosmic web. It is not a minor fluctuation, a quirk of measurement, or an expected empty patch of space. It is extreme in every sense, stretching the limits of what standard cosmology predicts. Its existence forces scientists to reconcile detailed observations of galaxy distributions, weak lensing mass maps, and the cosmic microwave background, demanding a level of precision and explanation that current theories struggle to provide. The quiet implication of this discovery is profound. Our maps of the universe are improving at a pace that surpasses our theoretical models. Instruments like LSST, Euclid, Planck, and the Roman Space Telescope are generating data with unprecedented depth, coverage, and resolution. We can detect faint galaxies, trace subtle gravitational lensing effects, and chart structures billions of light years away. Yet our theories, built to describe averages and expected fluctuations, are being confronted with anomalies that the models did not anticipate. The universe is revealing its complexity faster than our frameworks can fully explain it. This tension between observation and theory is not a failure, but a driving force for progress. Each anomaly, each extreme void, becomes a focal point for refining models, testing assumptions, and exploring new physics. The Eridanus Supervoid is more than a curiosity. It is a benchmark for what cosmologists need to account for, a reminder that the universe is still an unfinished dataset. With each new survey, the map grows more detailed, the anomalies clearer, and the questions sharper, revealing that the cosmos still holds surprises beyond our current understanding. Our understanding of the universe is evolving in real time. As telescopes reveal the interiors of voids, trace the faintest galaxies, and map matter directly through weak lensing, the line between known and unknown shifts. The Eridanus Supervoid stands as a monument to this evolving knowledge, a challenge that forces scientists to confront the limits of lambda CDM, inflation, and cosmic uniformity. It is a marker of the universe's unfinished story, signaling that as maps improve, the cosmos continues to defy simple explanation, compelling science to advance in step with discovery.